Resume. And from beginning. There are people online, yeah. It's not. Yeah, as far as I know. But we do have a couple people online. Okay. All right. Hard light, right? For a class of 27, we're missing a lot of people in person today. I don't know. What?
I think a new person, the person who joined late dropped.
Oh, okay. That may be. Okay, let's get going. We got lots to do. Do I have a PowerPoint, by the way?
Yeah, here.
Thanks.
There's extras around. I put them at the tables.
All right. So the plan for today is to keep talking about model fit and model adequacy because we did not finish that last week. I don't think we're going to get to predicted values today, but if we do, that's great. If not, we'll do that next week. Yeah, let's jump in. So things we did not talk about last week. Uh-oh. Oh no, I guess I did rearrange this. Okay. I don't think up until this point, we've talked at all about information criteria. So let's just kind of refresh our memory about what we have talked about. Last week, we talked a lot about estimation, remember? And we talked about, who remembers, what's the difference between FIML and REML? Full maximum likelihood and restricted maximum likelihood. Yeah, it has to do with one being conditional on the fixed effects and the other is not, right? FEML's conditional on the fixed effects. So what you need to remember, I mean, you don't need to remember all the gory details about, well, I don't even think I gave you all the gory details about estimation techniques, but what's really important for you to remember about full maximum likelihood versus restricted maximum likelihood is that there's good reason to prefer restricted maximum likelihood because with restricted maximum likelihood, it performs better in small samples, right? When we have small numbers of clusters. And again, I sort of gave that analogy of, computing the variance using the true maximum likelihood estimator, where you would take the sums of squares divided by n versus computing the variance using sums of squares divided by n minus 1. And actually, in a finite sample and small sample, n minus 1 will give you a less biased estimate of the variance. So you can sort of think of REML as being that way. So it's a technique that is actually should produce less biased estimates of the variance components, specifically really the variance components, when we have a small number of clusters. I think if you were to try to run things in REML and FIML, you would see that the fixed effects estimates would be really, really similar, if not identical, across the two estimation techniques. And in fact, if you were to run these models as multiple regression models, you would see that your fixed effects estimates would probably not be, I'm not saying they're going to be completely right, but they're not going to be that far off. But where the action really is in multi-level models is in these variance components, right? And we care a lot about if you haven't figured that out yet, we're going to talk again today about variances in a lot more detail. So we care about these variances. And so we really care about estimating our variance as well. And so if our taus are going to be underestimated, which is what happens when we use full maximum likelihood and we have a small number of clusters, that's a problem because we're spending a lot of time trying to actually explain those, to think about how do we explain this between cluster variance and our intercepts? How do we explain this between cluster variance and our slopes? And of course, if we don't have a good estimate of the between cluster variance and the slopes and the intercepts, then that's a big problem. So for that reason, we tend to favor restricted maximum likelihood over full maximum likelihood. And as I mentioned last week, there's this little quickie jiffy formula that gives you an idea about by how much your variance components might be underestimated. And it was really just a function of the number of clusters minus the numbers of fixed effects divided by the number of clusters. So if you have a small number of clusters, your variance components could be, fairly substantially underestimated. If you have a really large number of clusters, it's not going to matter much. So, when we do longitudinal analyses, for example, we'll often have hundreds of people. People are the cluster in a longitudinal analysis. So you might have hundreds of people in the sample. In that case, this REML-FIML distinction is going to be a lot less important. But in organizational studies, we've been using the HSB where we have 160 schools, but that's actually pretty big for, these kinds of studies. It's pretty common to have 20, 30, 40, 50 schools. And, in that situation, it's really going to make a big difference. So again, just to remind you, you might think, well, then why don't I always just do everything in REML, forget about FIML, and not think about it ever again? And the important thing is that we can't do any model comparisons of two models that differ in their fixed effects and use the deviances that are produced by REML. So we'll actually get different deviance estimates from REML and FIML. And remember that the deviance is this, it's the -2 log likelihood for the model, and it's really a measure of sort of the badness of the fit of the model. The lower the deviance, the better the fit of the model, but you can't actually do anything with deviance in isolation because, it's a function of a lot of different things, including the sample size and sort of the scaling of the variables and all kinds of other stuff. So you can't look at a deviance and say a deviance is high or low, but you can compare the deviance of two different models. But you can only compare the deviance of two different models that differ in their fixed effects if you've used FIML to estimate the model. But again, remember, REML is our default. So all the models that we've been estimating in REML, which is, a standard default in multi-level modeling for all the reasons that I just said. So, okay. So having said all that, I can use REML and use those deviances to compare two models that differ only in terms of their random effects, which again, we'll see lots of examples of that today. But I need to use the deviance that's computed with FIML to compare two models that differ in their fixed effects. And this becomes really important when we start to talk about information criteria like the AIC and BIC, because information criteria are computed using the deviances. And we need to be very careful to make sure that we're using the correct deviance to compute the AIC and BIC of interest. So, are you with me? So it's easy, right? It's really easy to get the FIML estimates if we need to get them. We can just rerun our models and say REML equals false. And we're lucky that ANOVA statement actually is always going to sort of rerun with FIML when we've run things in REML and we need to actually have the FIML-based estimates. So that's kind of nice. But if you just ask for the information criteria from R sort of just straight up, and you run your model in REML, but you really need the AIC and the BIC that are based on FIML, R is not necessarily going to be smart enough to realize that it should be rerunning the models based, using FIML. So in this case, you kind of have to remember, like, do I need the FIML-based estimates of my information criteria? So that's my sort of long-winded introduction to these information criteria. So the first thing is just to remind ourselves of REML versus FIML, which is super important when we're talking about model fit. And now let's talk about a couple of different information criteria that are commonly used. So the first is what's called the Akeki information criterion. And it's really sort of designed to sort of be sort of predictive, to sort of help us pick the right model and sort of help us pick the most sort of predictive model. Yeah, I guess that's all I really want to say about that. What I really want you to notice when we talk about these different information criteria, and there are probably 15, 20, 25 different information criteria. We're going to talk about the big three: the Akaki information criterion, the BIC, and the sample size adjusted BIC. All of these are a function of the deviance, which you already have, and the number of parameters that are estimated in the model. And so what these do, all of these formulas basically just impose a penalty based on the number of parameters in the model. So if you look at this formula, the AIC is just the deviance plus 2 times the number of parameters. If you think about that, what that means is every time you add a parameter to your model, then I haven't said the most important thing, which is we always, just like we always favor a lower deviance, we always favor a lower value for the information criteria. So we always favor a lower AIC, a lower BIC. So if you think about this, if I have 2 different models, right? I've got a deviance for model 1, I add a parameter. So it's a more parameterized, it's a more complex model now. So I've got a deviance for model 2, and the AIC is just going to be the deviance of the model plus 2 times the number of parameters. So if I add a parameter, right, how much does my deviance need to go down to favor that new model that has an additional parameter? 2, exactly. I mean, the math is actually really quite simple, right? So, what this is basically saying at its crux, and this is the way that I often find it useful to kind of think about it and look at it, is according to the AIC, for every parameter that I add to the model, the deviance needs to drop by at least 2 for the AIC to say, oh yeah, it's worth putting that parameter in the model, right? And now, if I think about that as compared to the likelihood ratio test, which we've already used, right? If I have a 1 parameter difference in 2 models, so I add 1 parameter to the model, and I use the likelihood ratio test, which is, remember, a chi-square difference test, what's the critical value of chi-square with 1 degree of freedom? 3.84, right? So, interesting. You see the issue, right? If I use the likelihood ratio test and I have 2 models that differ by 1 parameter, the more parameterized model needs to have a deviance that's at least 3.84 points lower than the deviance of the less parameterized model for me to say, oh yeah, that's the better model, right? If I use the AIC, I just need the deviance to drop by 2 points to say that the more parameterized model is the better model. So good news is that the vast majority of the time, I mean, if one model is a lot better than the other model, the deviance will drop by more than 3.84 points. And if let's say the deviance drops by 5 points, then obviously both the AIC and the likelihood ratio test would both point you in the same direction of saying, hey, you should favor the more parameterized model, the model that has more parameters in it, right? But what if the deviance drops by 3? It's like a nightmare situation. Because now the AIC says, oh, you should favor the model that has that parameter in. And the likelihood ratio says, no, you should favor the model where the parameter is not there, right? Where, you should favor the simpler model. So what do? I mean, this is where you as the researcher are really going to have to, think about this and look at holistically a lot of things in combination. So again, it's easy. When the deviance drops by a ton, more than 3.84 points, let's say in this scenario, although I haven't said anything about the BIC yet. So, it's easy, right? If the deviance drops by a lot, when you add a parameter, it's very clear. But if the deviance drops by just a little bit, more than 2 points, less than 4 points, now we're in a little bit of a stickier situation. Now, so the per degree of freedom penalty or the per parameter penalty for the AIC is 2. And you should just remember that because that's helpful to know. So the AIC is going to favor more parameterized models when we compare it to the other sort of biggie in the information criterion world, and probably maybe the most popular of the information criterion, is the Bayesian information criterion. The BI, which is the BIC. And the BIC, you don't have to be doing Bayesian, by the way, to use the Bayesian information criterion. And in fact, when you do Bayesian analyses, they usually use the DIC, but whatever. I know, which is a funny name for a criterion, right? I don't know if I would have named it that, but anyway, I digress. So the Bayesian information criterion is now the deviance plus the natural log of n is your sample size here, times the number of parameters. So where the AIC was 2 times the number of parameters, we're substituting in the natural log of the sample size. Oh God, okay, so you probably don't think in natural logs. None of us think in natural logs, right? But, you know, it's a number. And it certainly, the natural log will make the sample size, I mean, the natural log of the sample size is going to be much, much smaller than the sample size itself. But the bigger issue, I mean, because we can compute the natural log of the sample size, that's fine. But the bigger issue is, okay, that sounds good, but what sample size should I use? Because I'm in a multi-level modeling framework, right? So should it be the total number of level 1 units? Should it be the number of clusters? Should it be, remember how we talked about the N effective in the first week or two? This effective sample size, which was a function of our overall sample size divided by the design effect. Should it be that? Which would be, I mean, in some sense, that N effective is probably what most accurately represents the sample size that we have at our disposal given the interclass correlation coefficient. Well, I mean, again, this is one of those areas where I would say the jury is still out a bit. This is an area of active research. And what's really interesting is that different software packages will use different sample sizes. I don't know of a software package that uses the N effective, by the way, even though that's probably, in some sense, maybe the most logical. But some software packages will use the level 1 sample size to compute the BIC. Some software packages will use the level 2 sample size, and it matters because the natural log of the level 1 sample size is going to give you a much bigger number than the natural log of the number of clusters, right? Because again, you don't even have to know how natural logs work exactly, but trust me, if you take the natural log of something like 1,000, you're going to get a much bigger number than if you take the natural log of 30, right? I mean, they're both going to end up being probably sort of single-digit numbers, but you know, or low 2-digit numbers, but they're going to be radically different. So the correction for the BIC really depends on the way that you define the BIC, which, you know, is kind of problematic. And if we use the level 1 sample size, then the BIC is actually going to be usually, again, depends on your sample sizes, but it's generally going to be by far the most sort of stringent of the 3 criteria that I just talked about, the AIC, the likelihood ratio test, or the BIC. The BIC with a level 1 sample size will, and I've got some slides that'll show you what that looks like, will definitely impose a larger penalty than the likelihood ratio test or the AIC. So now, okay, there's a saying, like, if you have 2 watches, you never know what time it is. This is that kind of situation, right? Now I've got like 3 different ways of trying to decide whether I need this parameter or not. And I guess the good news is there are only 2 choices, need it or don't need it, right? But it's absolutely possible that you could find yourself in a situation where, you know, one of these 2 things says you need the parameter and the other 2 say you don't need the parameter, or vice versa. And in addition to that, you've also got the added complication of if you mess with which sample size you use, now you've also, right, like now you don't even have just, BIC is in some sense not even a unitary criterion, right? You need to make that decision about, are you using the level 1 sample size, the level 2 sample size, the N effective. Okay. So that's kind of the bad news. I mean, the good news is it means that you can use it means you have to be thoughtful, sentient person, which is good, right? but, okay. Last one that I'll talk about is the sample size adjusted BIC, or the EPSY, which is the deviance plus the natural log of n star times p. So notice instead of n, we put in n star, and n star here is n plus 2 divided by 24. We still have the same problem about which n. Should it be the level 1 n? Should it be the level 2 n? Should it be the n effective? And then we're going to take whatever that n is, we're going to add 2 and divide by 24. So if you look at that formula, you can see that, again, assuming I'm using the same n, the correction for the SBIC is not going to be as stringent as, or like the penalty, I shouldn't say correction. The penalty for the SBIC is not going to be as high as the penalty for the BIC, right? If you take the same n and you add 2 and you divide by 24, you're going to get a smaller number than if you just take n, right? Does everybody see that that's true? So the SBIC, often you find yourself in a penalty world that's somewhere between the AIC and the BIC. And by the way, do not ask me why it's n plus 2 divided by 24.
Just kidding. Let's do that.
I have spent years of my life trying to figure this out. If anybody finds out, please let me know. I mean, I've gone so far as a couple years ago, right before COVID, I was at a conference and Larry Hedges was there, who's like, huge name in stats. And I went up to him. I think I must have had a beer or something. And I said, can you please tell me why the adjustment in SBIC is n plus 2 divided by 24? And he muttered something, but it was, he was like, I don't know, it probably has something to do with something. But he didn't know. So nobody seems to. Somebody knows. It's out there somewhere. But, don't ask me to explain it. I'm not, so for that reason, I'm not a huge fan of the SBIC because I don't really understand the correction. I mention it because it does get a lot of play. Okay. So another thing to think about. Okay, so I've said all that. Another little like hitch. I didn't say, remember how last time when we were talking, I made this big deal about how we should, when we use the likelihood ratio test, that the actual penalty for the likelihood ratio test is not quite right when you're looking at variances, because variances are on the bound, right? We have these boundary issues with variances. And so do you remember, I had a whole slide that sort of showed this is the chi-square that you would use for fixed effects, and the actual sort of like corrected chi-squares for when you're actually looking at a random effect, or evaluating random effects or variance components, is actually a little bit lower. And I haven't said anything about that here. Again, the information criteria literature doesn't really address any of that at all. As far as I've ever read, when people use information criteria, they just use information criteria, and the penalty is a per parameter penalty, whether it's a fixed effect or a random effect. So I guess bottom line, I would say, I think the information criteria can provide you with some guidance. Again, the idea is that it should be sort of, they should be helping point to the best model. But they're not always going to point to the same model, and they're certainly not infallible. And as I said before, the likelihood ratio test, the AIC, the BIC might disagree about what model to favor. And in that place, then you really need to think about, you really need to use your professional judgment, which model you favor. And I think, as I mentioned last week, we're not just going to use model, I would call these our model fit criteria, but we also want to look at model adequacy, which are not the same thing. So, model fit is really about, right, sort of how well the model, it's about the model data fit. But anybody who's been in SEM class knows that you could have a really, really good model fit, but you could be explaining basically nothing in the outcome variable, right? So we don't want to just think about model fit. We also want to think about the adequacy of the model. So, for example, if I'm trying to decide whether to include a randomly varying slope in my model, it does make sense to look at the deviance, the deviance test, right, the likelihood ratio test, and the information criteria, which give me an idea about whether the fit of the, how the fit of the model compares. But let's say I put in a randomly varying slope, and that randomly varying slope, what if it didn't actually explain any of the variance in my outcome variable, right? So like, that would be important to know too, right? Like you can put in a randomly varying slope, but maybe, just because you say it's randomly varying, well, it doesn't make it so, right? But maybe when I actually estimate the slope variance for that randomly varying slope, maybe it's super small. Maybe it's near zero. Again, sadly, I don't have any good statistical tests to tell me whether it's statistically significantly different from zero or not. We talked about that last time too. But maybe it is very, very, very close to zero, right? Or maybe it would actually be zero in the population, right? So I don't want to include randomly varying slopes that are basically zero or near zero, for a couple of reasons. They unnecessarily complicate the model. They will cause me to have problems. They will often cause me to have problems estimating the model. So when you start doing multi-level modeling on your own, with your own data, it's not uncommon to find a situation where the model won't converge after whatever the default number of iterations is. So, you're running this model and it's like just really slow to converge, or it doesn't converge at all, and eventually says like you've maxed out on the number of iterations and you still have non-convergence, which means, remember last week we talked about convergence. Does anybody remember what's convergence? Not really. Okay. So remember, we're sort of iterating back and forth, right? We're sort of going back. And when we get to a point where we're not, we're using this iterative procedure to kind of come up with our parameter estimates, right? And then sort of feeding those back in to see how well it fits the data, and back and forth and back and forth. And at a certain point, like, there's not going to be a change, or there's not going to be much of a change as we're sort of going back and forth in this iterative procedure. And that's really what it means when the model has converged. And you can set, we're going to use the default, but you can set the convergence criterion in a program. So you could say, I need the change between these two iterations to be, 0.001 or less, to say it's basically zero. There's nothing's changing anymore, right? Or you could change it and make that, say, that criterion is 0.01 or 0.1. I mean, you wouldn't want to make it too big, but I mean, you theoretically can change the convergence criterion. But what will often happen if you've put in a randomly varying slope, I mean, it could be an intercept too, but it's not usually. Like usually when there are problems, it's problems with the slopes, not the intercepts. So when you put in, when you say, I want this slope to randomly vary across clusters, and there is really no or almost no variance across the clusters in terms of that slope, I mean, think about it. You're asking this program to kind of come up with a good estimate of this variance that is near zero, right? Or is zero. And again, we talked about, it's like, that's also on the boundary of the parameter space. And so it becomes this really difficult problem for the program. And it will not always come up with a reasonable solution. And so often you'll run a model and it just won't converge, which is a really frustrating thing, by the way, because you imagine it's your dissertation and you run this model, right? And then you wait around for a while and it doesn't converge. That's like not a suitable solution, is it? You're not going to say, well, sorry, I collected all these data, but the model didn't converge. So I guess I don't know.
This isn't going to go well.
That's right. That's right. You've got to, so my experience is, by far, the most common reason that a multi-level model does not converge is that that you're trying to estimate a randomly varying slope that has basically no actual variance. And so when you remove when you say, I'm not going to estimate a randomly varying slope for that slope, things work like a charm. Okay, well, that's fine. And that's great if you only have one randomly varying slope in your model, because you can probably take a pretty good guess that it's that slope that's the problem. But what if you have a model where you have, like, 6 varying slopes, and you try to run the model and the model doesn't converge? So, and again, I've been there. I've had this happen. So then you say to yourself, oh, one of these, model has not converged. So that's, maybe I don't have as much information about how things are going as I might like. And I'm pretty sure it's probably that one of these slopes is a slope that I don't need. But how am I going to know which slope I don't need? I mean, honestly, then you're kind of in a bit of you found yourself in a mess. And this, again, goes back to why I said last week, you don't want to, by default, just put in all possible slopes as randomly varying, because that's a recipe for non-convergence. And then you're going to be stuck where you're like, okay, I don't need at least one of them, but I don't know which one it is, right? And you can imagine, you start going through and going, what about this slope? What about this slope? What about this slope? That feels a little, that feels like a kind of a questionable research practice to me, right? That doesn't feel like a great way to do your data analysis. So it's going to be really, really important that you think, again, in this class, I'm going to give you lots of examples of homework problems where we compare models, right? We sort of make judgments about whether we need slopes or not by comparing models. But when you're really doing this, and you will do model comparisons, by the way, in real life. It's not like I'm teaching you model comparisons and you'll never use them. But in real life, it's really important to start out with what you think is the right model, and not to just say, I'm going to default to putting in every possible slope that I could have, and then I'll figure it out later. You may think about it really hard, put in the set of slopes you think you need, and still have to think about it later because you were wrong, but it's really important to do that up front. Yeah. If you have only fixed effects and no random effects, you don't even have a multi-level model. So no, you have a multiple regression model, and you wouldn't have an iterative technique there, right? So the thing that separates a multi-level model from just a regular old multiple regression model is that you have one or more random. Most multi-level models have randomly varying intercepts. If you and this is I can remember a time when I ran a model, actually. So I ran a multi-level model and had a randomly varying intercept. And then I put in a whole bunch of predictors. And after this doesn't happen very often, by the way. This is like the exception rather than the rule. Don't expect this. But after putting in a whole slew of predictors, I was actually able to explain all of the variance or most of, like pretty much all of the variance in the randomly varying intercept. So basically that meant I could explain all of the between school variance and math achievement, let's say, using mean SES and sector and I don't know, whatever. It wasn't math achievement. It wasn't the HSB, but you get the idea. So I had a slew of variables and I was able to explain all of the between cluster variance and the intercept, and I didn't have any randomly varying slopes. So this was a long time ago. This is when I first started doing multi-level modeling too. So I took out the, which you would do. I took out the randomly varying intercept, and then voila, you don't get a deviance anymore, right? You get, the program will run. It'll still, but you'll get results, but you don't necessarily get a deviance. And the results that you get are absolutely identical to the results that you would get if you ran it as a multiple regression. That's what you get, and that's what it is. It's a multiple regression with cross-level interactions or whatever. You have those. So yeah, so you need a random effect. To be a multi-level model, you need at least one random effect. Yes.
The thing about statistics as being both proactive and reactive. So like proactive and reactive perspective, I think of it as like statistical surgery. And this is what we're kind of dealing with on the back end. What things from a research design point of view could help make sure that convergence is hit more?
Well, I think it's really important that you conceptually think about, and this is again, as a substantive, like as a methodologist, I might not know the answer if I'm working with somebody else on their project, but the substantive researcher should have the answer about, do I think that I expect this parameter, this slope, let's say this SES slope. So let's think about the SES slope for a second, because we keep talking about it. So this is the effective SES, right? And again, when I say effect, I don't necessarily mean it as causal, I mean it as more predictive, right? But this is the effective SES on math achievement. Do I think that, or think of it as the relationship between SES and math achievement. Do I think the relationship between SES and math achievement, do I think that relationship is going to vary across schools? And not just vary across schools, but vary across schools after accounting for whatever level 2 variables I think might also help to predict that relationship, right? So in our example that we've been using in class, we've been using like mean SES and sector. So do I think that the relationship between SES and math achievement after accounting for sector, so holding sector constant, right? And after accounting for mean SES, right? Do I think that after accounting for those two things, that there would still be random variation in terms of the relationship between SES and math achievement? And I think the question is, if yes, why? Articulate. You should be, the researcher should be able to say, yes, I think so. Even after accounting for these variables, I think there'll still be random variation because there's this other variable that would also explain the variation that I haven't included in my model. And I think it would be a big predictor of differences in slopes, or because whatever. I mean, I think the onus is on the researcher to be able to come up with a reasonable sort of story a priori about why you would expect there to be random slope variance. And I think if you can't, then I think it's dangerous to just sort of say, well, I don't know, let's just throw it in and find out, right? So I think that's how we need to be proactive. And this is where I think, I hear people say sometimes like, oh, you can't really pre-register, modeling studies. You can't really pre-register SEM or multi-level studies, to which I would say, no, that's absolutely false. You absolutely can pre-register studies. And it is true that, when you're doing the analyses, there are these decision points that come up. But when you pre-register a study, you would say, right, if you were to pre-register a multi-level study, you would say, this is my model. These are the slopes I'm going to allow to randomly vary. And this is why, right? These are the slopes I'm not allowing to randomly vary because I don't have a substantive reason to think that they would, right? And then the next part would be how you would determine whether you actually need the randomly varying slopes that you substantively believe you need, because that would be a reasonable question, right? So it's like, which ones do I substantively think I need? How am I going to determine whether I need those or not, right? And so what we're talking about in here is, in this class, I'm going to give you all these ways of determining whether you need slopes or not. But that isn't to say that you should always just start out by throwing them all in. It's like you should have a small group, like you have, a slope, and you're trying to, you had 9 independent variables, you only allowed 1 to randomly vary. And the question is, does that one even need to randomly vary, for example? Yeah. Are you asking for a conceptual rationale or a statistical one? Okay, so when we haven't gotten to growth modeling yet, but when we get to growth modeling, you're going to see that we're going to sort of reframe these models so that it depends on how you center things, but the sort of the standard way of centering the intercept is actually going to be where people start, and the slope is going to be people's growth rates. And people are going to be the cluster. And I think that's a perfect example of like, okay, I don't actually think everybody in my sample is going to grow at the same rate. So I am going to default to allowing my growth slopes to randomly vary across people, right? And, you know, again, there could be a scenario in which after you add all of these person level predictors, you're actually able to explain all of the between person variance in the growth slopes. And you don't need to allow for that random variation after you account for, you know, whatever, you know, X, Y, Z, PDQ, all of these variables. But by certainly at the outset, and like by default, I would definitely be thinking people vary in terms of their growth rates. Sure. Okay. So, yeah. So I think I've said everything I wanted to say about that slide. Okay, so here's just a graph that kind of shows that the decision values for like AIC, BIC, and chi-square difference measures. And here I'm agnostic about, like, I just have BIC. I have the sample size, so it's BIC with whatever that sample size is, which could be a function of cluster, N effective, or N. But what you see here is that, like, with a sample size of, for example, you know, what is it, 100 over there, you can see that the BIC already is, that's the top curve there, right? You can see that the BIC already has a much larger penalty than the chi-square difference test or the AIC, right? So you can see, like, the AIC penalty, no matter what the sample size, is 2. The BIC penalty, no matter what the sample size, is 3.84. That's why those are straight lines. And then the BIC penalty, with 100 people, the BIC penalty is like just over 4.5. And when you get to like 2,000 people, again, because you're taking the natural log, so you're getting this kind of, yeah. Okay. Sorry about that, people who heard that crash. But you can see that no matter how big the sample size is, the BIC penalty is never really going to get bigger than 8, right? Because you see how it's kind of like, so that's why I said, like, you know, the penalty is going to be in the single digits, but you can see that even with 100, with a sample size of 100, it's already a larger penalty. And I think in the chapter, we talk about how small the sample size has to be to have the penalty for the BIC be lower than the AIC. And it's like, I think 7 or 8 or something. It's really small. So anyway. Okay. So now this graph is showing, you know, again, we've got 3 different BIC values, and the chi-square difference test, or the likelihood ratio test, and the AIC, looking at the critical decision values as the number of parameters increases from 1 to 10. And the important point here is that the critical value of chi-square changes, right? So like if we have a 1 parameter test, the critical value of chi-square is 3.84. But when we do a 2 parameter test, and again, I'm assuming not variances here, right? I'm just doing the uncorrected ones. When we have a 2 parameter test, the critical value of chi-square is 5.99. So if you think about that, that means that that's basically a penalty of about 3 per parameter when you have a 2DF test, whereas it's just under 4 per parameter when you have a 1DF test, right? And the cool thing about the chi-square, you know, chi-square and degrees of freedom is if you actually get to a high enough degrees of freedom with the chi-square, the critical value of chi-square with that number of degrees of freedom is just going to be a little bit more than like the number of degrees of freedom. So you get to something that's like the ratio is going to be just over 1. Of course, we're never going to do a test that has, like, you know, in multi-level modeling, we're never going to do a test that has like 100 degrees of freedom. That would be like a really, really big random effect structure to have pared down or whatever. That would be crazy. But the point is that the penalty, the per parameter penalty remains the same in the world of information criteria. But when you use likelihood ratio test, the per parameter penalty actually changes as a function of the number of parameters. You follow what I'm saying? Again, you're thinking, I don't know. Do I care? Maybe you don't care. But all of these things enter into why you're going to get different decisions when you use these different criteria, right? So, these are important things to think about. Okay, so here we go. Model fit, this table shows model fit criteria penalties for models, and really we're generally not going to have models that differ by much more than 4 parameters, usually, when we're doing this. So we've got the penalties for models that differ by 1, 2, 3, and 4 parameters. And you can see, like in AIC, right? If you have models that differ by 1 parameter, the penalty is 2. If it differs by 4 parameters, you can see the penalty is 8, right? BIC with an N of 10. So you could imagine now that when I have an N of 10, I'm using the number of clusters, let's say, instead of the number of people, and I have a small model. And you can see that even with the cluster size of 10, the BIC penalty is already bigger than the penalty for the AIC. So like if, right, if the BIC favors the more parameterized model, then the AIC must also favor the more parameterized model, right? But that the reverse is not necessarily true because, right? Okay, the likelihood ratio test for variances, you can see, so the 1 parameter test would be like 2.71, 2 parameters is like 5.14, and when you get up to 4 parameters, it's like 8.76. The likelihood ratio test, sort of the traditional likelihood ratio test, you've got, 3.84. When you get up to 4 parameters, it's 9.49. So again, now you're like less than 2.5, sort of a penalty of less than 2.5 per parameter on that traditional likelihood ratio test. And if you look at the sort of the BIC with the sample size of 10 and that 4 parameter test, looks very similar to the traditional likelihood ratio test, right? And the likelihood ratio test with the variances is actually going to be sort of the least conservative of all of those. But you can see that this changes radically depending on what your BIC measure, or like how many people you have, right? So if you have 100 people, the 4 parameter test, you're going to need a deviance difference of 18.44 people. And if you had 10,000 people, the deviance difference test, you'd need a deviance difference of like 36.84. So again, imagine you're doing a 4 parameter test and you find that the difference in the likelihood rate, or the difference in the deviances is like 9, let's say. That's like you're in the netherworld of trying to figure out what is, So we have to be really thoughtful, and we have to lay out how we're making this decision, and right, and we need to look at these multiple criteria, and we sort of need to weigh them and make a reasoned judgment and explain our reasoned judgment to others so that they can follow our logic and understand why we did what we did. And I think that's super important. All right. So model fit's a lot messier in multi-level modeling than I don't know, it's really messy in SEM too, but it's obviously more messy in multi-level modeling. Okay, so back to our question that I sort of posed last week, which is like, do we need to include this random effect in my model? Do I need this randomly varying slope or not, right? Do I need to estimate these variance components? And so here's what I'm going to tell you need to think about as you make this decision. And these are the things I would want you to think about as you make this decision on your homework, okay? We can compare the fit of the 2 models using a likelihood ratio test, right? Which we've talked about a lot and we will continue to talk about. There are 3 different ways, actually, we can compare the fit of models using the likelihood ratio test. We could use the ANOVA function, which we've used. I'm going to talk about the RANOVA function today. And we can use test bar, which I'll talk a little bit more about today too. We can compare using information criteria, which are that's not the same as using a likelihood ratio test, right? The But we could use information criteria like the AIC, the BIC, and I would say the first two bullet points are really about model fit. And then the third thing is I could look at, like I could be looking at how much between, I can look at a couple different things. I can look at like what proportion of variance, or how much variance is there between clusters in terms of my slope, right? After accounting for everything else in my model. So I can be looking at some of these proportion of variance explained measures. So like how much have I reduced the variance is good, but also then how much variance remains. And, is this proportion of variance that's explained by the randomly varying slopes, is that enough variance to sort of cause me to think it would be a real mistake to drop the randomly varying slope, right? Because again, you can sort of imagine you have a randomly varying slope. If I told you this randomly varying slope explains 5% of the total variance in math achievement, which I don't know, maybe you would think 5% isn't that much, but 5% is actually a lot. So I'd be like, whoa, 5%, the randomly varying slopes explain 5% of the variance in math achievement, like in my total outcome variable. I don't think I want to lose that. That seems like I should do that. I should keep that. But what if I told you the randomly varying slopes explain 0.1% of the total variance in my outcome variable? Then you might be like, I could write maybe part like 0.1% is not that exciting, right? It's not a life or death research study. Again, I always like to say that, 0.1% when you're doing life and death research, every 0.1% counts, right? But like kids in schools, 0.1%.
Whatever caused that cost millions of dollars.
Well, there's that. Well, yeah. But this is just, that's true too. But do I need to account for that 0.1% by allowing the slopes to continue to randomly vary? That's a judgment call on your part, but I think it's pretty easy to see that you could imagine that number could get low enough that you're like maybe you'd say 0.1%, I still care. But what if I said, how about 0.001%? Do you still care? 0.00001%. There's probably a number I could say where you'd be like, okay, I'm with you. I don't care anymore. Let's fix that slope, right? Let's fix that slope and move on. Yeah. It's an excellent question. So theoretically, because the fit and the variance explained aren't necessarily going hand in hand. So yeah, theoretically that could happen. And one of the reasons that it doesn't sound as crazy as it might on the outset is that one of the big drivers of deviance or the -2 log likelihood is actually the sample size. And so, it's just like anything else in statistics. If I have a big enough sample size, you know how in stats, if you have a big enough sample size, even trivial effects can be statistically significant, right? I could have 1 million boys and 1 million girls, and the gender difference could be 0.001, but because I have 1 million boys and 1 million girls, that actually ends up being statistically significant, right? So the same thing kind of can come into play here, that I could get a really big change in the deviance because I have just a ginormous sample, but the reality is that it's a really this random slope explains such a trivial amount of the variation sort of that it, yeah, so it could happen. Yes.
Models, each of them had an AIC, IC. Or are we comparing the difference between the two? If we're comparing two models, is it just with the deviance, we're looking at the difference?
Oh, so with the AIC, so again, with the AIC and the BIC, you just are always looking for, it's not, with the deviance difference test, we actually compute the difference and then we've got a critical value, but with AIC, BIC and all the information criteria, it's just lower is better. So you can just look at the two AICs and whichever AIC is lower is better. Now that's also if you think about it, a little problematic in the sense, because of everything that I just told you, right? If you run two models and the AICs are 0.3 point, it's 0.3 points lower in the one model than the other. Even though it is again, technically from an AIC perspective, lower is better, but On the other hand, it's like, yeah, okay, well, it was like this, like this much lower. But yeah, there isn't any kind of like set number or anything. With the BIC, you'll sometimes hear people talk about, BIC differences between like, I don't know, like less than 5 being smaller and more than 5. I mean, sometimes people use these gestalt things that's with the BIC and say like the bigger the difference, the bigger, sort of the more the one model is favored, which I mean, again, I think it's fair for any of these. The bigger the difference, the more compelling evidence there is favoring one model. But there is no actual cut point for the AIC and the BIC. It's just lower is better. Okay, so when we talk about proportion of variance explained, we'll kind of revisit the Rodenbush and Bright framework, and we're also going to talk about the Reitz and Sturba framework, which is going to come in handy for us in terms of thinking about some of this stuff. Okay, so we've talked about ANOVA, right? We've talked about this ANOVA function, but we can, and I won't talk too much about this in the PowerPoint because I'll show it to you when we get into the our markdown, but there's also this RUNOVA function, and this is actually from the package Elmer test, and it's a likelihood ratio test that compares models that differ in terms of their random effects. So if the model's fitted with REML, the tests are going to be basically like REML-like likelihood ratio tests, and of course, if you're comparing models that differ in their random effects, you can, remember I said you can use REML, so that's fine, so there's no issue there. And you'll get something that looks very much like the ANOVA table that we had, but we're going to get tests of the random effect terms. And, that's okay. It's kind of good. It's kind of nice. I mean, the downside that I see for RUNOVA, as compared to like the test var function that we'll talk some more about today, is just that there's nothing in either ANOVA or RUNOVA that takes into account that correction for the critical value that we should be using because we're talking about variances, which you would think RUNOVA would, because it's all about variance components. But as far as I can tell, it's using just the sort of the standard cutoffs. And as I mentioned last week, the reality is the vast majority of the time that is not going to matter, because it's really only when we find ourselves in that small slice of statistical significance between like 0.05 and 0.077 that we're going to find that using the standard likelihood ratio critical value is going to give us a different answer from using the one that's actually corrected to be considering the variances. So if you run something like ANOVA or RUNOVA and the p-value is 0.1, you don't really have to worry about the correction, right? And if the p-value is less than 0.05, you don't have to worry about the correction. It's just when you're in that small space between 0.05 and 0.077 that, using the correct critical value will give you something different from using the incorrect critical value. So we do need to kind of keep thinking about that when we use both ANOVA and RUNOVA. But I'll show you how to use RUNOVA. It's kind of nifty. It basically what it'll do is you just take, rather than ANOVA where you compare two models, and this is probably the nice thing about RUNOVA. So in ANOVA, you have to compare the two models, right? And it gives you the chi-square difference test. In RUNOVA, let's say I have a model with a randomly varying slope, and I can just run that one model, and then I can say, like, RUNOVA and in parentheses model 1, let's say that's the name of my model, and it will, like by default, say, oh, you want to compare, you have a randomly varying slope. So you want to compare this model to a model without a randomly varying slope. So it'll basically like eliminate the randomly varying slope and compare your model to the model that doesn't have a randomly varying slope. So again, that's going to be a 2DF test, which is another difference between that and like test var. But so that's what it'll do. It basically just like takes your model and it tries to reduce the random effects by structure.
Randomly varying slopes. Will it take them all out?
That's a really good question, actually. I don't know that
Have ever used that
I don't, I've never used it with more than one randomly varying slope. I think it'll probably take them all out, but we could play around with that and see.
Yeah.
Yeah, I mean, right, we could figure that out. And then there are a whole bunch of, I like on the markdown, I have a whole bunch of different sort of like, if you use, if you have, because you can specify a slope that varies, but does not covary with the intercept in R, right? And what happens when you use Renova if you've already specified that there's no correlation and that kind of stuff. So I have all of that on the R markdown, but generally speaking, we're going to use it with like, a slope, and we can just kind of compare it to a model that doesn't have a slope. If you actually have a random effect, only a random effect for the intercept, then it will remove the random effect for the intercept. But again, you remove the random effect for the intercept and that's all you've got, then you're really talking about having a multiple regression model. So, but you can compare the fit of those models. Okay. So, so using this test bar, which you all have had experience with now. So, using this test bar to test the slope variances, the logic here is just that, the test of the slope variance is really a joint test of the slope variance and a slope covariance, right? And so I might want to break out and see, if I could eliminate one of those two components, or, yeah, I mean, if I might want to see if I could eliminate one of those two components, or I might want to just at least be able to break out and see how much of the change in deviance is attributable to the covariance versus the change in deviance that's attributable to the variance, right? So basically, what this test bar thing does is it just breaks the omnibus test into pieces. So you can actually look at, like, do you need the covariance or not? And then do you need the variance or not? But the big downside to this test bar thing is that it also currently only works for one slope. So if you have more than one randomly varying slope, you're not going to be able to use the test bar function. And, I had high hopes about rewriting it so that it would work but I didn't have time to do that. And I don't know if it matters that much, but okay. So we want to determine, whether we need a particular slope variance, right? You could sort of imagine there are three models that I might want to think about. This full model that has the slope variance and the covariance. I could compare that to a model that has the slope variance but no covariance, right? And in that's going to be test bar, whatever the name of your model is, slope, the name of your level one variable and then you say test cov equals false. Okay, so now I'm not testing the covariance in that model. I'm really just I'm eliminating the covariance. And then the no slope variance, which eliminates both the slope variance and the covariance. There you would say test var model slope test. Oh, wait a minute. I totally messed that up because they both say false. Correct. Wait. Help me out here. I can go to my R markdown. I think it should be true, false.
And then false.
True and then
Yeah.
false, right? So, that's a big typo. Yeah, I was going to say that doesn't make sense that it would be test cove is, okay, so it should be true, test cove is true, test cove is false. Yeah?
Successfully, and then I was
Uh-oh. Okay. Oh, yeah, we haven't even really talked about the boundary singular fit. And it didn't run at all?
So I was able to do one of them, but then in my homework, I'm just like, well, I guess I'm not going to be able to run that test with the false one, but the boundary singular fit, see helps in singular.
Yeah. Well, a lot of times you'll get that error message from R, but it'll still run the model anyway. But not in this case, not in this case. Okay, well, this singular model fit thing, most of the time, or much of the time, it actually relates to exactly what we've been talking about in class, which is, I mean, think about it, boundary, model, singular. You're on the boundary of a parameter space. You're trying to estimate a randomly varying slope that isn't estimable, right? And so the vast majority of the time when you get that error message, which often, again, often in R, you'll get the error message, but it'll run anyway. But that's actually a sign often that you don't need that randomly varying slope. But sometimes it yibbits completely and it just like chokes, right? So did it do it when the covariance was constrained? Test covariance, yeah, when did it do it? Did it do it with?
So I was able to successfully run it when the test covariance was true. And it didn't work. True again, just to see if it was that same. So
Well, that's weird. So it ran and no, so that's really funky. So it ran, then it didn't run, and then it continued to not run. Yeah,
like 2 or 3 times.
and it didn't work. Okay, well, we'll have to kind of problem. Yeah. We'll have to problem solve that.
I made my temporary variable.
I'll buy that.
Even if the values were the same, the p-values were different. Even though the like columns comparatively to two different centered.
Well, yeah, but that makes sense because it matters how you, or wait a minute, are you saying that columns were the same?
The way she like
I'm saying,
included the
like,
center.
In one version, I made my own group by from like the way we learned it. In one, I used your SES mean and it ended up with different percent.
But wait a minute, did you have, but when you look at the columns, they looked identical. Oh, well, that's, well, yeah. I mean, that is weird. That is weird. I don't know why that's, yeah, I don't know why that's happening. I will have to, weird things with test bars.
And it's highlighted, we'll look at it.
Yeah. So, I mean, don't freak out, people, if you had trouble with test bar, because we hadn't really gotten fully into test bar. So we're going to downweight that question substantially. But I think that the logic, and again, like in some sense, I don't even care. I should probably not have said you have to use test var, because I don't even really care in the grand scheme of things whether you use test var or not. What I care about is that you understand the logic of this testing procedure, which is the full model has the slope and the intercept, right? You could imagine comparing 3 models. You could do it using test var. You could do it longhand. It doesn't actually matter, right? Test var was just a shortcut way for people to be able to do that. And the only nice thing about test var, actually, over like Renova or something else, is that it uses it does use the p-value correction for the variances. And that is the only package that I know of that has built in some sort of correction, like actually thinking about the p-values with the correct critical value for the chi-square, right, or whatever, the likelihood ratio test that takes into account that the covariance, and remember, I don't know if I said this, but I should say this. So when you're doing these tests, the covariance does not have boundary issues. Only the variance does. So that's the other really interesting thing about this 2DF test, right? I think I mentioned that last week, but this 2DF test, when you're checking whether the covariance is equal to 0 or not, that should have a critical value of 3.84. Like that's just because a covariance could be positive, a covariance could be negative. So if the hypothesis is that the covariance is 0, that's fine. Like that's not actually a hard statistical test to kind of come up. The hard statistical test, the hard test for us is to test variances. Variances are hard to test because 0 is on the boundary of the parameter space, because variances can't be negative. And so what you're saying is my null hypothesis is that this thing is 0, but it's sitting right on the verge of inadmissibility. right? So like, I want to test this null hypothesis that it's 0, but it can't go lower than 0, right? That's the essence of the problem when we're talking about this stuff. And that's why, like, when you think about testing significance for variances, it's really tricky, right? Or also thinking about like whether we need variances in or not. So again, the logic, forget about test bar for a second, but the logic is we got a full model with a slope and intercept, they both randomly vary, and there's a covariance. I want to know if I need that randomly varying slope or not. There are actually sort of 3 models I can think about. The full model has the slope, the intercept. Oh, can I draw on here? This full model, I'm really saying that my tau matrix is tau naught, tau naught 1, and tau 1, 1. Right? This is my tau matrix for the full model. Okay? Slope variance only model, what I'm saying is, and remember I told you, I said, be really careful about these models. Don't default to this, okay? But in the slope variance only model, I'm constraining this covariance to be equal to 0, right?
This case, I'm sorry, number 2 is true or false?
I think it's true. Well, let's
So
look
I
at
think it's the other, yeah, that's what I was,
It's on the next slide.
I was gonna say, why guess when we have it on the next slide? Hold on, how do I get to the next slide?
I'm awesome. Now I'm confused about test bar, so
There
I
we
don't
go.
know what we.
There it is. Slope variance, yeah, this is right. Slope variance, but no covariance to a model that does not contain the slope well, okay, does not contain the slope variance or the covariance, right? So test code, okay, the test code that's false is slope variance, but no covariance that does not contain, okay, so hold on. So I'm not jiving with my slides here, so I apologize for that.
Yeah, so I thought, okay,
So hold on.
yeah. I'm on the same page as
Just
you.
so I can make it.
Okay, so hold on. Just, I need like a blank piece of paper. Full model is slope variance. Forget about what this says. Forget about test bar for a second, okay? Let's just talk about these 3 models conceptually, and then we'll go to the next slide and talk about how it works with test bar. So we got a full model, right? The tau matrix is tau naught, tau naught 1, tau 1, 1. This is the model that that is by default the model that I'm fitting. The 2 alternative models that I'm going to fit are, okay, a model that does not have a covariance, but still has an intercept variance, and a model that has neither, right? These are the three possible models that I'm interested in, right? Is everybody there? Does everybody kind of understand that? So we've got a full model, we've got slope variance, slope covariance, and we've got an intercept variance, right? We've got a no slope variance model, which eliminates both the slope variance and the slope covariance.
So there's just an intercept variant.
Just an intercept variance, right? And then the middle model in between those is a model that says, okay, well, maybe, because this is a 2DF test, like this, when we normally eliminate a slope variance, we go from here to here, right? Because we eliminate this entire row. And the whole idea here is, okay, but like, what if I want to know, what is this, I want to know how much, and this is where the logic is like, so bear with me. I want to know how much is like attributable to each of these pieces. Like, I really want to know how much can I attribute to the covariance and eliminating the covariance, and I want to know how much can I attribute to eliminating this, right? So what we're going to do is actually, we've got these three different models. So yeah, let's go to the next slide. So in test code false, we're comparing a model with slope variance, but no covariance, to a model that does not contain the slope variance or the covariance, right? So here we're really comparing like a model that has, here if we say yes, we favor the model that has the slope variance, but it doesn't have the covariance in there. So that, from what I was just talking about in the last slide, is comparing models 2 and 3, right? Everybody, so I'm comparing a model that has a slope variance but no covariance to a model that doesn't contain a slope variance at all. So I'm comparing models 2 and 3.
So you're seeing if you need the slope variance.
I'm seeing if I need the slope variance, but only the slope variance, because in all of these other tests, I'm really testing a 2DF model where it's like the slope variance and the covariance. And it could be the case that I only need the variance and I don't need the covariance. And because it's a 2DF test, it could be the case that, like, when I look at it sort of omnibus, I don't realize that, right? Because for example, the 2DF test, it has a chi-square change, a chi-square critical of, what is it, 5.19 or something, right? But the 1DF test has a chi-square critical of, what was it, 2.71 or something, right? But think about this, like in those three models, so I've got tau not, tau not 1, tau 1, tau not, nothing here, tau 1, and then just tau not, nothing here, right? So imagine that the deviance goes down when I go from here to here, but what if it doesn't, or like it goes down a little, but it doesn't change that much, let's say, when I go from here to here. But like, what if, like, how do I disentangle how much of the model misfit that from here to here? How much of it is a function of constraining the covariance to 0, and how much of it is a function of constraining the variance to 0? That's the essential question that we want to know, right? Like, how much of a problem could I just constrain the, like, what if I could just constrain the covariance to 0? Like, and then I compare that to this. What is that 1DF test of just the variance being 0 without having the covariance in there? That's what I want to know, right? And then the covariance is like, okay, now I want to know what happens if I constrain the covariance to be 0. Well, I can't constrain the covariance to 0 if I don't have the variance, right? So constraining the covariance to 0 has to be a comparison of the covariance of 0 to the full model. And constraining the variance to be 0, I want to compare the variance is 0 to a model where the variance isn't 0, but the covariance is 0. Because what I'm trying to do is basically step through 3 models that are each like just 1DF. Well, I guess the first model is whatever, but like I'm just going 1DF at a time. So I really just want to see like how much does the model, and remember, I'm eliminating stuff here. So the question is, how much does the model fit to grade? So how much does the deviance go up when I eliminate the covariance? How much does the deviance go up when I eliminate the variance, having already eliminated the covariance? And if you want to know how much does the deviance go up by eliminating both at one time, like you can do that with RENOVA, right, or ANOVA. Yeah. Yeah, I did. I mean, yeah, I'll get a piece of paper.
Is, are you in like?
Well, here, I hear some white space. I'll use this.
No, like the actual.
No, it's not the model. The model is the same. It is this. This is all we're doing.
I think he wants to know how you tell R to do that. Is that what you want to know?
I'm thinking just like what the equation
would look like when we're talking about betas and.
No, that's what I'm telling you. It doesn't change that at all. The only change is here. And again, if you don't like test code, I don't really care. You don't have to ever use test code again. But what I do want you to understand, and I think is really important, is the logic of these three models, right? So we've got a full model. All three of these models, they look identical in terms of the fixed effects. They look identical in terms of our code up until you get to the random effect structure, right? The stuff that happens in the parentheses. Because the equations are identical. They're absolutely identical. But what we're doing is we're messing with the random effects. We're messing with the variance components, the structure of the covariance. So in the first one, this is the full model, right? And in this case, this is where we would actually say, right, like SES and then whatever our cluster ID is, right? And then in the second one, we have no covariance. And then in the third one, we don't have a matrix anymore. We really just have found not not, right? And so in that case, just saying, one cluster ID, right? And in this case, I have the R code and the R markdown, but in this case, what we generally do is we sort of separate out into the two different parts of the parentheses, like we say SES cluster ID, right? Do you remember that? We have some code like that, plus like one cluster ID, and we do that in a way so that R is saying, oh, you want a randomly varying slope and you want a randomly varying intercept, but you don't want the covariance between them. So that all happens in the random effects structure of the model. But if you were to type out the equations for all three of these models, like the kinds of equations that people report in their papers and stuff, the equations are identical. They're absolutely identical. The model equations, right? Because we're only talking about models that differ in terms of the random effect structure.
And so is the full model, is that testing the intercept?
Yeah, so I was just gonna say, can we go back to test var when you put in the model? Doesn't it test a model with the intercept only, or the variance of the intercept only, and then without it? Because that's how you're testing the variance of the intercept. And if it's not, then I told everybody a lot of wrong information yesterday, because I'm pretty, I was sure that's how test var worked. So apologies if that is not right.
Oh, testing if you put the intercept in, it's testing the variance of the intercept.
But if you put intercept, or if you just put the model, it gives you the same thing. So if you put test var model 1, you get the same result as if you specify intercept.
Because I think that's the default, right?
Right, so test var mod 1 is the test of the intercept variance. Okay,
Right.
then I told you guys all right.
Yeah.
I was getting nervous for a minute.
Yeah. Everything that we've been talking about here has been the test var where you've got in quotes the slope,
Yeah. Okay.
right?
Full model is just testing the intercept. However, we were moving out the covariance and the slopes if the full model is just testing the intercept.
Well, the way that I just told you.
If it's only testing the intercept, just I would just does not mean the slope and the covariance are already. I get that makes me think the slope and the covariance are already removed. If we're just testing the intercept.
You mean like command, where you just put model on?
Put test bar model 1, like you said, that was where it said that's sort of the intercept one. Doesn't that give us all of them?
Right, I don't think it's actually, so I think that when Betsy's talking about the three models,
Yeah.
that's different than the three commands, right? Because each
Yeah.
command is comparing two models.
Yeah, exactly.
So the testing, and Betsy, correct me if I'm wrong, but when you say test true, I think that it's testing just the covariance compared to one
But that doesn't, yes, exactly.
without it,
Right,
right? And then the slope, false
Slope.
is just the slope.
Yeah, so everything I've
And
been
then-
talking about here is with the slopes. But let us can we not get completely sidetracked on the test code and the homework? Because we're gonna get into the R markdown, and I think it's in there. It'll be a lot easier to talk it through in R markdown than to spend like another 15 minutes going back and forth, like on the board, talking about test code, because it's in the markdown. So do you see the logic? All I care, I mean, again, I don't care. I won't grade test code. I will not grade that question. You all get a free points on that question. All I care about is, do you understand the logic of these three models? Because this is what's important. That's not important. This is important.
All we wanted were the points on that question.
You got the point. And like, by the way, I mean, if you go to the last slide, you'll see there's a plea for me, for you to be thinking sentient beings when you're doing your modeling. That's all I really want from you. So forget about test bar. Do you see the logic of these three models? Yes. Okay. I will show you how to do it later in R. But for now, it doesn't matter about R. I just want you to understand the three models. Yes.
And this extends if we have multiple slopes. The one.
The logic, not test bar, because the test bar cannot handle multiple slopes. But the logic remains, and you can set up the model to do the same logic, whether you use test bar or not, right? Because the logic remains the same. Like you could have a full model where you have two. Uh-oh, that's bad. Can't see my last tower there, but right, but you could use the same kind of logic of like, okay, I want to eliminate, let's say, tau 2,2. If I'm going to eliminate tau 2,2, I'm eliminating three parameters now, right? So I could, how much of eliminating tau 2,2, how much of the model misfit is attributable to like getting rid of these two covariances versus how much of the model misfit is attributable to getting rid of the variance. So like, could I get rid of these two? Again, I mean, like I don't want to make too big a stink about it because as I told you before, I think in the grand scheme of things, all other things being equal, you should default to unstructured covariance matrices. I think it's kind of dangerous to like, get too far down the path of like not using unstructured covariance matrices. But if you did want to like actually eliminate covariances and keep the variance, this is exactly what you would want to do. You would want to say to yourself, okay, well, how bad is it if I eliminate these two covariances, but I keep the variance? Like how much model misfit is there, right? How much does the deviance increase if I get rid of these two? And if the deviance doesn't really increase at all, then you could make a compelling argument that you could get rid of those covariances, right? But if the deviance does increase quite a bit, then that, even a reasonable amount, then that would be sort of a sign to you that you probably should not do that. Yes.
Essentially, what does from the full model when you're testing the intercept, which one's being like crossed out essentially if you're.
Let's not worry about that one right now. Let's wait till we get to the R markdown and do all that. I think. Because again, this is really what we're most interested in right now. These three models, like testing the intercept is going to be getting rid of the intercept, but that's not as interesting. Okay. We good? Okay, it's 10:30. Well, yeah, I'm just FYI. Okay.
So the unstructured is where you estimate all of them.
Right?
Structured is where at least one thing is constrained.
Yes. I mean, yes. There are different structures, but yeah. So there's unstructured. Like I would say that the the one where you have sort of the off diagonal elements constrained to be zero, that's sometimes called like an identity structure or diagonal structure. But theoretically, you could actually have even crazier, like, you can mess with things to have even crazier sort of structures than that. And of course, if you get rid of both the slope variance and the covariance, then that's not necessarily unstructured anymore, right? Okay, yeah.
Would the U not be a constant? Like gammas, or would those not be?
if you're, not sure if I follow the question. If you constrain tau not to be zero, then you're constraining the variant, then you're saying that you don't need a randomly varying intercept. Yeah. Okay. I guess I will not start this before our break. Let's take like 10-minute break, come back and do, we'll probably go into the markdown stuff actually. I'll go get those. All right. No, I don't want to see. Okay. Okay. Let's get back to it. We need to get through some of this R squared rights and Sturba stuff. So I do want to talk through the PowerPoints, a few of the PowerPoints, then we'll turn over to the R markdown code. And I was thinking about the test of R thing over the break, and I was thinking, it's a helper package, right? But it's obviously not helping you. So that's something to remember in general in R. And there are a lot of ways to do things, and there are a lot of different helper packages that people create. But if a helper package doesn't help you, then it's not worth using. But I really do believe if you understand conceptually what we're talking about, then we can help you through the R code. That's not such a big deal, but you really need to have a conceptual understanding of the models that we're talking about. And I'm sorry that R makes it so difficult for people to I know R is it's a steep hill to climb. I get that. I do. Believe me, even I've climbed it myself. But, is not a class about R. It's a class about multi-level modeling. So I really want you to focus on the concepts, and we will get you through the R. If you understand what you're doing, we can help you figure out how to do it. But if you don't understand what you're doing and you're just trying to parrot something off something else without understanding what it is or why it is that way, then that's when it's much harder to help you. So, all right. So having said that, I don't really have much to say about this. R squared. We're used to thinking about R squared, right? And you can think about R squared, I guess, in a couple different ways, just in general. You can think about it as being like, what's the proportion of explained variance, right? Or you could sort of think about it as what's 1 minus the proportion of unexplained variance, right? Okay. That's just a real basic precursor. So we've talked about Rodenbush and Brake's proportion reduction and variance statistics. You remember this, right? And these require comparing two different models. So we've got this baseline model, right? Or sort of the more parsimonious model minus the more parameterized model, right? And then we take the variance component from the baseline model minus the variance component for the more parameterized model divided by the variance component for the baseline model. And that gives us like this proportion reduction in variance by adding these new things to the model, right? But we have to compare two different models to get anything like these R squared measures. And the other big downside to the Rodenbush and Brake measures is that they actually can be negative because, unlike in single level models, you would never get a negative R squared, right? But there are scenarios in which you might actually find that the variance increases when you go from a less parameterized model to a more parameterized model. And in that case, you're actually going to get a negative proportion reduction in variance. And when that happens, usually what people do is they just fix it at 0. Because, if you get something that's like negative 0.1%, you're just going to call it I'm not reducing the variance at all. But of course, it's troubling to people to get these negative measures, but that's like a sign to you that it's like a pseudo R squared measure. It's not a true R squared measure. It's really about the proportion reduction in variance across these two models. And the time that is going to happen, by the way, the most common scenario for getting something like that is when you group mean center a level 1 variable and you compare a model without the group mean centered variable to the group mean centered model. So it's just like it happens. It's just a thing. So Wrights and Sturba came along in 2019, and this is my favorite paper of 2019. And they said, like, hey, we could actually think about how the total variance in the outcome variable. We can think about how to partition the total variance in the outcome variable into these different pieces. And once we partition it into these different pieces, then we can create a whole slew of true R-squared measures. And so this kind of revolutionized the way that people were thinking about proportion variance explained in multi-level models. Okay, so we're about to this too much, but all I'm saying here is that y sub ij is a function of, right, we've got some variables that have fixed effects, right, and we've got these gammas, and then the w's here are, these are actually, right, we have variables that have randomly varying slopes. And if you think about when we write out the combined model, remember how, like, if you have SES, like group mean centered SES, and the slope is randomly varying. Remember how when you write out the combined model, you actually get U sub 1j times SES? So that's really what this part of this equation is just saying, like, okay, we've got, right, when you sort of think about the model, we've got variables that have fixed effect, right? Like the gammas are really about the fixed effects, and it's like gamma times this like SES variable, right? We've got the fixed effects for SES. But then we also have these u's, and the u's actually get multiplied by like, well, 1 for the intercept. But if we've got randomly varying slopes, they're going to get multiplied by these level 1 predictors. So like, yeah, you don't have to worry about sort of the matrix notation here, but I'm just kind of explaining how this works because it is going to kind of come into play when we think about the Wrights and Sturba. So basically, right, our gammas are our fixed effects. And we have these level 1 predictors that have random slopes. And the level 1 predictors with random slopes here are the W's, and the random effects are the U's. Okay, so we can kind of think about, our model as breaking out that way. And then again, you can trust me on this a little bit, but I can say, okay, this model implies something about, so we have model implied total outcome variance. So like I can use the model to basically come up with what is the total variance in my math achievement or my outcome variable. So that's the variance in y sub ij. And it's model implied because I'm using the model to generate all of these pieces and then I'm adding them together and that should give me the total variance in the outcome variable. But it's all like based on my model-based estimates. And what they say is, well, they don't just say this. I mean, Snyder's and Bosfield, lots of people have said this before, but you can sort of, you can break the total variance into these pieces. There's the variance that's explained by all of the predictors via the fixed slopes. So these are gammas. So these are your gammas, right? So how much of the variance is being explained by your gammas? Just think of this as that. How much of the variance is being explained by the fixed effects? This, which looks ugly, I know, is how much of the variance is being explained by the randomly varying slopes, the variances and covariances of the randomly varying slope coefficients. And this is something that we're going to think is really interesting because I was saying like, well, we want to sort of see like, are my randomly varying slopes actually explaining a lot of variance or not? Because if they're not, maybe I don't need them, right? So kind of hold on to that. D is going to be important to us. And then this is just the variance that's explained by the randomly varying intercepts. And then the last piece is the variance that's not explained. So let me say that one more time. Variance that's explained by my fixed effects. Variance slash covariance that's explained by my randomly varying slopes. Variance that's explained by my randomly varying intercepts. Variance that's not explained. And I take those 4 pieces and I add them together, and that should give me the total variance. Yeah.
So
Mm-hmm.
also
Oh, the third one. Yeah. The randomly varying intercepts, which might be cluster means or might be intercepts, depending on what's going on in your model, right?
Yeah.
Yeah. If you had nothing else in your model, it'd be fair to say cluster means, but once you've got a conditional model, they're really the randomly varying intercepts.
Okay.
Yeah, sure. So okay, so that's cool, right? So I can use it. So I can actually figure out what each of these pieces are. And then I can take any one of these pieces and divide it by the total to get the proportion of, just like it. Now this really is like it. This is really an R squared now. Although again, I'm using model applied total outcome variance, but I could take F and I could divide it by my total. And that's going to tell me what proportion of the outcome variance is explained by the fixed effects, which is kind of like a regular old R squared from a regular multiple regression model. So like F divided by the total is the proportion of variance explained by my predictors, like by my fixed effects. So that's super interesting, right? I like that one. B divided by the total is also really interesting because this tells me what proportion of the total variance is explained by randomly like the slope variances and covariances, right? So I can get an idea here about, how much variability is my randomly varying slope or are my randomly varying slopes explaining in terms of the outcome variation. And obviously, remember what I said before the break, if they're not explaining much, like if this ends up being something super close to zero, that would be an indicator to me that like, oh, maybe I don't need to allow that slope to randomly vary because allowing it to randomly vary isn't actually explaining any of my outcome variance, right? So like this is kind of like your regular, this is kind of, I feel like, closely aligns to the way we think of R squared in a multiple regression. This becomes, I think, hugely important from like a diagnostic standpoint about like, do I actually need those randomly varying slopes or not, right? Which is kind of like the theme of the day. I feel like we talked about that quite a bit. And then this tells me about, okay, again, after accounting for everything else that's going on in the model, like, how much random variability is there in my intercepts? Which, again, is that explained or unexplained variance? It depends, I guess, on the way you look at it. It's explained by school membership, but it's unexplained by your predictors, right? So certain people, and then of course, this is clearly variance that's not explained by anything. It's not explained by school membership. It's not explained by the randomly varying slopes, and it's not explained by the fixed effects. Does that make sense? So probably like these are two of the ones that we're going to, now what they, hold on. Let me keep going. So then they say, okay, then they say, well, you know what? We could actually break out the F into the variance that's explained by the fixed level 1 predictors and the variance that's explained by the fixed level 2 predictors, right? And now an important thing to kind of keep in mind is that any predictor that has like a level 1 component in it is going to be that's going to be variance that's explained by the level 1 predictor. So like when you have a cross level interaction, let's say between mean SES and SES, right? If you think about it, because it's a cross level interaction, it really has to do with this level 1 SES variable and how that's moderated by mean SES. But it still is, if you think about it, that's still a level 1 predictor, right? So basically, variance explained by level 1 predictors is going to include level 1 variables and any interaction that includes a level 1 variable. So like if there's a level 1 variable in there anywhere, it's going to get fed into F1, and F2 is really going to be about the level 2 variables. Yeah. Mm-hmm. Well, not always, because like if we could, when we have mean SES in our model, for example, we have mean SES predicts the randomly varying intercepts and mean SES predicts the randomly varying slopes, right? So we have sort of, often you have like this, sort of a gamma naught 2 times mean SES is the effect of mean SES on the intercept. That would feed into this. But like, let's say gamma 1, 2 mean SES times SES cluster mean centered, let's say, right? That is, even though mean SES is in it, it's still got a level 1 variable in there. So it's really about a level 1 predictor, right? It's about how the level 2 predictor moderates the level 1 slope. But any of the level 1 slopes would go into F1. Okay. So we could break those out that way. Now I've got 5 components, and I can use those 5 components to examine variance explained. And that's kind of interesting too, because now I can say, well, how much of the variance is explained by the combination of level 1 predictors, right? What proportion of the variance is explained by the level 2 predictors, et cetera, et cetera. Okay.
N is that random intercept and B is that random intercept and slope. So what's the difference between those two intercepts?
Well, it's really random slope. It's really random slope variation and covariation. Get rid of the intercept there. This is really the intercept variance. I was thinking slope variation, and it also includes covariation, potentially with like the intercept or whatever, but get rid of that. It should really be variance explained by random slope variation and covariation. Okay, so we can combine these 5 things to come up with different R² measures. And then if you read their paper, it gets like a little overwhelming because when you start combining things in different ways, you can come up with like a million R². So they're like, hey, you could have the proportion of total variance explained by the level 1 and level 2 fixed effects, or you could have the level 1, right? The proportion of the total variance explained by, the level 1 variables, or the proportion of the total variance explained by the level 2 variables. And of course, you could say, what's the proportion of variance explained by the randomly varying intercepts or the randomly varying slopes? So they come up with like, I forget how many different R² measures. And then, so here are some more. Then they say, oh, you know what? If you cluster mean center your data, you can really divide the variance into within and between variations. And so if I cluster mean center my data, and then I add the aggregates back in at level 2, I could decompose the total variance into level specific variance. And so then they come up with a whole slew of level specific R² measures. So how do they do that? Okay. So basically, again, we have talked about this. We have the variance explained by the level 1 and the level 2 predictors, right? We have these 5 components, but what they say is, okay, what would belong at level 1? Well, level 1 would be F1, not F2. That's level 2 only, right? And the variance explained by the random slope variation, that's definitely level 1. Intercept variance, that's definitely level 2, right? It's like how the intercepts randomly vary. And this is definitely level 1 residual variance, right? So basically they're saying, okay, if you want to kind of say what proportion of the level 1 variance are you explaining with your fixed slopes, you could just take F divided by F1 plus B plus sigma squared, or sorry, it should be F1. F1 divided by, so like this gives me what proportion of the within variance, of the level 1 variance is explained by the fixed effects. And I could do the same thing at level 2. Now level 2, we said there are only 2 pieces. At level 2, it's just F2 plus M. So if I wanted to know what proportion of the level 2 variance my fixed effects at level 2 explain, I could just compute a proportion of variance like that. I could say, okay, it's F2 divided by F2 plus M. And again, like, cool, I think it makes sense. I think where things get a little overwhelming is that because there are these 5 components, you can start to put them together in a lot of different ways, right? And so their first paper, I think they have 12 different R² measures that they mention. And it's just a lot. But I think if you understand what the components are, then you can be like, okay, well, that kind of makes sense, right? So the big thing is, are we talking about the total variance in the denominator, or are we talking about level specific variance in the denominator? And then, what proportion of variance are we interested in looking at, right? And so we can look at that way. So again, the next so this just shows that. So this is I have a whole slew of slides that basically say, what are these measures, right? Which we just talked about. We could look at the total variance explained by all the predictors via the fixed slopes, and we could look at that at level 1, or we could look at that at, well, actually, that's not here. This is the total variance explained by the random slopes, right? Total variance explained by the cluster-specific outcomes, and so on and so forth. I'm going to go through all these. I think you get kind of the idea of the components. These may confuse you more than they help, but the important thing is that you really understand the 5 components that we're kind of putting together. So I'm going to show you how to do all of this in our, I do want to give a word of caution about the rights and Sturba stuff though. So I am a big proponent of this rights and Sturba framework. In recent months, I guess, I've become less enamored with the level specific variance components. I think there are some problems, potential problems with the level specific variance components. Specifically, they don't seem to work well when the number of people per cluster is small. So I think this whole thing works really well asymptotically, which is great. And so if you have a large number of people per cluster, I think that breaking into the 2 different levels works really well. But if you have a small number of people per cluster, then I don't think that the partitioning into the level specific variances works nearly as well as one might like. Having said that, the total variance measures still work great. So I think in the homework, I think I really, I'll show you some level specific stuff in the R Markdown, but I think in the homework, I really focused on just total variance explained measures. And I think there are only 2 that you have to compute.
Yeah.
So, all right. So having said that, let us turn to our R Markdown file and talk about how to do some of this stuff. I don't want to save that. Okay. So you should, I hope, all have gotten the week 5 folder. Get the week 5 folder. Yeah, here it is. The week 5 folder. And if you open up the Markdown folder for week 5, and you should also have a big Markdown file for week 5. So okay, there we go. So the first thing I'm going to have to do is just do some housekeeping and, call my libraries, right? I don't even need all of them, but I'm going to call them all anyway. Turn on, okay. And then I don't know if I need these functions or not, but I will do that anyway. Okay. So right now I'm just kind of getting set up. Okay, and now I'm going to use that same HSB file that we've been talking about, and I'm going to read it into R. I don't even really want to view it, so you can view it if you want. So I'm going to read HSB in. Great. Okay. And then I've got to create all my little grand mean and group mean centered variables. Kind of annoying, but you can save them out. I thought about doing that, but then I was like, I did actually create a file like that, but okay. More group mean centering. So all of this stuff is stuff that has not changed at all since week 1, 2. Overall SES. Oh, because we didn't run that. Not bad. Okay, there we go. Okay, and then I actually am going to create, this is the first new thing today. We don't really have to do this, but just for simplicity, I'm going to create another data frame that just has the variables that we're going to be using for the rights and Sturba stuff. And you'll see why this is kind of nice later. So all this code does, you're not necessarily going to need to ever use this, but all this code does is say, okay, I'm going to create a new data frame. I'm calling it HSV2. And it's going to be HSV minus, this means get rid of these columns, minus, really like a, you know, whatever, columns. Think of it that way, this right now. And so I'm saying get rid of column 1, 3, 4, 5, 7, 9, 10, 11, 13, and 16. So I'm getting rid of all of those columns, just so I have like a nice, and you'll see actually. So let's go ahead and do that. And if you look, there you go. I have this nice little data frame now that is actually just the variables that I'm going to be using. So I could be using, and I better be careful, I could use HSV or HSV2 to run my models now, because actually HSV2 only has the variables that I need. All right. Okay. And I just left the code here too. We don't actually need to do this right now, but if you wanted to like write out that like data frame as a CSV to save for later, this is the code you could just use. Okay, so we don't really care about that. So let's go back to our model from last week. So we've got model 6, and I'm going to run that. And let's look at let's remember what model 6 is. So we've got math achievement, right? And we've got math achievement, the function of, look at our summary. Actually, that'll help us. Here we go. Right? So we've got math achievement. It's predicted by SES, which is, remember, it's group mean centered. And then I also have mean SES predicting the intercept. So this is what I mean by like, when we were talking before about what would be a level 2 only variable versus a level 1 variable for Wrights and Sturba. SES, CWC, level 1 variable, right? It's centered within context. It's definitely level 1. Mean SESC, level 2. It's mean SES predicting the randomly varying intercepts. Everything's happening at level 2 there. This is a level 2 predictor. Sector, same thing. Sector is a property of the school, doesn't vary within schools, and it's predicting the randomly varying intercepts. That's a level 2 variable. SES, CWC, by mean SES, that's a cross-level interaction between SES, clustered within context, and mean SES. So even though mean SES is a level 2 variable, from a like variance standpoint, this is actually explaining, right? This is actually cross-level interactions would be counted within like level 1 variance. It's explaining, because it's explaining how mean SES moderates the effect of a within level variable on the outcome variable. And because there's this within level variable, that makes this level 1, right? It's like the moderational effect of a level 2 variable on a level 1 variable. Yeah.
So, just with like about mean SES as predicting randomly varying intercepts, like if with this slope over here, this is showing the fixed effect of mean SES, right?
Mm-hmm.
So,
But that's what the fixed effect of mean SES is. The fixed effect of mean SES really is, it's mean SES is a level 2 variable. Because it's a level 2 variable, it can only explain between cluster variance, right? So, and it's a level 2 variable that's explaining between cluster variance in what? In the intercept. That's really what it is. Whereas here, this is mean SES, a level 2 variable explaining between cluster variance in what? In the randomly varying SES slope. Yeah? So if it just is like mean SES by itself, like we will often say it's the effect of mean SES on math achievement. People say that all the time. So like, you know, that's fine. People say it. But really, it is really the effect of mean SES on the randomly varying intercepts. If you sort of think about the combined model, that's really what we're talking about, right? We're talking about, you know, we've got like, I got, you know, beta sub naught j is equal to, oh no, what did I do? That is not what I wanted to do.
did it.
Okay, but yeah, probably, and I really, there must be a way to draw this thing, but apparently not. But like beta sub naught j, right, equals gamma naught naught, that's my overall intercept, plus gamma naught 1 times mean SES, which, so if you think about it, that's the effect of mean SES on the randomly varying intercept, right? Should I
Want
write
us to
that?
write it up here?
Yeah, write it on the board, write that.
Let's say it again, because, hold on.
Does that make sense? So like, again, that's why I like the multi-level equations, because. Yeah.
Tell me, or do you want to write it? Or just tell me
I'll
again?
write it. This is a
Okay.
good one though.
I don't know.
So beta sub naught j is equal to gamma naught naught plus gamma naught 1 times mean SES dot dot dot, right? Whatever else. So like, what are these? Are the randomly varying intercepts. And so I'm really saying gamma naught 1 over there is the effective mean SES on the randomly varying intercept. Now, remember this then gets like plugged in the combined model. And so we are going to be eventually using this to predict math achievement, but it's sort of doing it via the randomly varying intercepts. Because it's a between cluster variable, it can't possibly explain within cluster variance. It can only explain between cluster differences either in the intercepts or, again, if we have this, right, in this case, now mean SES is explaining between cluster variance in the randomly varying slopes.
So if you included mean SES, not as an interaction, but as its own term in the,
That's what this is.
like, in, like,
And that's what that is, when it just says mean SES all by itself. Then it's always, I mean, it's always true that if it's its own term like that, and it's a level 2 variable, then it's fair to say it's the effective mean SES on that achievement. But it's also fair to say, and technically more accurate to say, it's the effective mean SES on the randomly varying intercepts. Yeah, thanks. Sure. Okay. So, okay, what if I want to know? What if I want to know, is this SES slope, is it statistically significantly different? Oh, well, actually, that's a different question. Okay, well, I think I mentioned this at the last class. If I wanted to test whether the SES slope is statistically significantly different from 0, or in Catholic schools, right? Because I get this SES slope when sectors equal to 0. So this tells me that the SES slope is statistically significantly different from 0 in public schools, but it actually doesn't tell me if the SES slope is statistically significantly different from 0 in Catholic schools. So if I wanted to do that, how would I do that? The easiest thing is actually just to redundant code sector. Right? So sometimes you have to think about, like, sometimes it's easiest to recode things a couple of different ways to get the statistical test that you want. So that was kind of my only point there. More important point for today's lecture is, okay, I can see that the correlation between the slopes and the intercepts, right, the randomly varying slopes and intercepts, I can see that correlation is 0.39. But what I don't know is if that correlation is statistically significantly different from 0. And the sad thing is, like, it might be really tempting to just be like, well, can I just like eyeball it and say, like, if it's really big, then that must be statistically significant. But unfortunately, it's really not fair to say that, because oftentimes these covariance components are not very precisely estimated. Like, if you think about what we're doing, it's like, oh my gosh, until this semester, you had like one residual variance in multiple regression. Now we've got like this massive tau matrix, and we're trying to estimate all of these elements of the tau matrix. And so the covariances are sort of the hardest to estimate in some sense. Or, they often are estimated the least precisely, I guess I should say. So I have definitely seen scenarios in my own work and in other examples where, like, the covariance between the slope and the intercept is in the 0.9s. but it's actually not statistically significantly different from zero because it's just such a noisy estimate. So like if you put a confidence interval around it, the confidence interval is like negative 0.9 to positive 0.9 or whatever, you know, something crazy like that. So, so this is one of the reasons again that we, you know, if we want to interpret that covariance, like, and I would argue in organizational models, we often don't care, but in longitudinal models, we really do care. So if we want to interpret that covariance, then we, you know, then we need to sort of think about like, is this, you know, is it fair to interpret? Is it statistically significant, right? Okay. So the next thing that I did is just create like a data frame that has my variance, covariance, like my variances and covariances in it. So we can see the variance covariance matrix, which is actually kind of nice too. Now we can see the variance covariance for SES and it'll never show up on the summary. Okay. All right. So what if I want to force the covariance between the slopes and the intercepts to be zero, right? So what if I wanted to force the randomly varying SES slopes and the intercepts to be uncorrelated with each other? Then I could compare the two models, right? The model that has that covariance and the model that doesn't have the covariance, and I could compare the two models to see, like, you know, how much does getting rid of that covariance worsen the fit of the model, right? And now here I'm just sort of saying, like, you know, be careful. That Doug Bates, who came up with the Elmer package, says, like, it's really important to be careful about, don't by default just get rid of those covariances, because the covariances, you know, the covariances are a function actually of where the variables are centered and all kinds of other things. So it can actually cause problems for you and make the, you know, the model fit. The model fit, if you constrain, let me say it this way, you constrain the covariance to be equal to zero. If you change the centering of the model, those models will no longer be equivalent because it means something, because that covariance has changed, right? And so, like, you could imagine if I centered it, imagine centering somewhere where the covariance is actually close to zero, then maybe the model fit would be similar across those two models. But in another model, maybe the covariance is actually quite large. And so when you constrain it to be zero, the fit of those, you know, the fit of that model gets much worse. So that's kind of crazy if you think about it. But like, depending on how you center your variables, the model, you know, having a model with a covariance constrained to be equal to zero does not necessarily give you equivalent models. But that's not true, by the way, if you don't constrain that to be zero. So that's like a good reason to not default to constraining those covariances to be zero. Does that make sense? Kind of? Yeah. So yeah, here are my three models that I'm interested in. Model 6 is this unstructured tau matrix. That's what I was talking about before. We've got 3 taus that we're estimating. And we're allowing them to randomly vary and covary. You can imagine one where model 6A, where I constrain the slopes and the intercepts to be uncorrelated. So that's one parameter fewer than model 6. And in model 6B, I'm constraining the slopes to be 0. The SES slopes are not randomly varying. So that is 2 parameters fewer than model 6, 1 parameter fewer than model 6A. And these are the models that I was talking about before the break, right? So I've got unstructured tau matrix. Here I've got, you know, sort of like a diagonal tau matrix where I've got taus on the diagonal and I don't have a covariance. And here I only have 1 tau now, right? I mean, I have a 1-by-1 matrix, which is really a scale. So, okay. Now here, and there are a variety of ways that you can actually write this code in R. But one of the ways that you can write the code in R to constrain the slopes and the intercepts to be uncorrelated with each other is to use this double bar. Probably the easiest way, actually. So this double bar says, like, if you look at this, and remember we said the equations are identical. The first part of the model is identical. And the only difference here in my coding is SES, here in the random effects part, I'm just saying SES underscore CWC double bar, school ID. double bar that says estimate a randomly varying intercept and a randomly varying slope for SES, but don't estimate the covariance between the two of them. So that's how we do, again, there are a couple different ways to do it in R. This is probably the easiest way. It's just to put in a double bar. So that's going to give me model 6A. So now I can run that model. Okay, and now it's totally fair, right? Oops, there we go. On that model, now it's totally fair to compare model, oh, let me do this. Compare. I really like this compare thing because it's pretty. It does line up nicely. There are things I don't like about it, like the fact that we get standard deviations instead of variances. That annoys me. Right, so here are variance components. Just keep that in mind. These are all in standard deviation units right now, not in variance units. But okay, here's our model, and you can see, like, here's our model 6, right? And we have this correlation, and model 6A, like, they put these on different lines because it's just the way that the R code is working, but really these are both the same thing, right? That's the variance component for the randomly varying slope. This is the variance component for the randomly varying intercept. Here I'm estimating a correlation between the slope and the intercept. And now I'm comparing two models that differ in their random effects, not their fixed effects. So it's totally fair for me. It's telling me Dremel, which is nice. It's like reminding you, these are the deviances that are computed using Dremel. But because we're comparing models that differ in terms of their random effects, I can compare the model fit of these two models using Dremel, right? And so now I see that the deviance is 1 point lower in the model that includes the covariance. So, okay, so yeah, forget test bar. Tell me, you can tell me with this. What does that mean? Which model would I favor? The model, well, the model with the lower deviance always? The model with the lower AIC or BIC always. But remember, deviance, we do the likelihood ratio test. And this is a covariance, by the way. So my critical ratio would be 3.84. So according to the likelihood ratio test, I would want this deviance to drop by at least 3.84 to favor the more parameterized or the more complex model. If the deviance drops by less than 3.84, again, if I'm using the likelihood ratio test, then I would favor the simpler model. If I were using AIC, which we said was like the most generous, the most liberal in terms of, pointing us to more parameterized models, if I use the AIC, remember that the AIC invokes a penalty of 2 per parameter, right? So the AIC here, I could compute. It would be, well, I don't know what the number of parameters is, but I could figure out what the difference in the AICs would be really easily, right? I have 1 fewer parameter here, so I would need the AIC to go down by at least 2 points to favor the more parameterized model. And because this is just a 1 parameter change, right? Then I only get, it only goes down by 1 point instead of 2 points. That means that the AIC would also favor the simpler model, right? Which is model 6A in this case. Is everybody with me? So if I use the AIC, the BIC, the SBIC, the likelihood ratio test, even if I messed up and used the likelihood ratio test with the critical value for variances, wouldn't matter. Under all of those scenarios, just a 1 point change in the deviance when I eliminate 1 parameter says, that's not enough of a change in the deviance to make a case for like going with the more parameterized model. These models essentially fit about the same. That's really what we're saying. The fit is not statistically significantly worse by eliminating that parameter. And if the fit isn't statistically significantly worse by eliminating that parameter, I'm going to go with the simpler model, which in this case is 6A because it's the model that doesn't have that covariance, right? So there's one fewer parameter. Everybody with me?
For models going from less to more complex, we're actually reversing that and going from more complex to less. I think that's like the, like I said,
Well, you can do that. We can go from less to more.
it's like presented in your slides is like, we're starting with unstructured, which is like more complex, and I'm used to having like.
Going the other way. Yeah, yeah, but it doesn't, but I see what you're saying, but it doesn't matter, right? It's always, whether we go from less to more or more to less, it's always that, like, in the moment, it's the comparison. And it's like, the less complex model, we're gonna favor unless the deviance drops by enough for us to say, oh yeah, we need that complexity. And the question is, what is drops by enough? Well, God, we talked about that ad nauseum before break, but I know that 1 point is not drops by enough, right? No matter how you cut it, 1 point of a drop is not going to suggest favoring the more complex model. Is everybody with me? So right now, 6A, that's the model. So again, 6A is the model where I have two taus, but I have no covariance component, right? So I have this diagonal tau matrix.
And the only change is the double bar.
And the only change in the code was the double bar. The double bar did it. That's it. And the double bar said, just don't put in a covariance there. Okay? So now, I can run an ANOVA here. Ta-da. And here we go. When I run the ANOVA, it actually gives me the AIC and the BIC, right? So I could see here which one has the lower AIC, model 6A, which one has the lower BIC, model 6A, right? Here's our log likelihood, and if you multiply that by -2, you'll get the deviance, right? And then we see like the difference in the deviances between the two is actually 0.9. I mean, it doesn't show decimals here, but if it did, we would find that it's 0.9 with 1 degree of freedom. The p-value is 0.34, which is not statistically significant. So for all of those reasons, I'm going to favor model 6A, right? Does that make sense? Okay. All right. So now I could also, right? I could actually take model 6 and I could use this test bar and say test cove equals true. And that will give me a test of the statistical significance of that slope intercept covariance or slope intercept correlation, right? So it's a 1DF test, and it's going to test whether the covariance between the slopes and the intercepts is statistically significant. And I start with model 6 where it has, has that in there, right? And I run my test bar. Runs eventually. Why are you being so slow? Okay. All right. And it's a 1DF test, and it's again telling me, it's telling me this is not statistically significant. So I would favor the model that does not have the covariance in there, right? Okay. Okay. So now I've got let's do RANOVA, by the way. Okay. So if I run RANOVA, model 6, so it looks just like ANOVA, but again, we only have one model. It says ANOVA-like table for random effects, single term deletions. Now be careful, single term deletion means I'm deleting one term, but it doesn't necessarily mean I'm only deleting one parameter. So, you can see here that I'm getting, what's it deleting? It's deleting the randomly varying slope in this term. So I use model 6 and it's eliminating the randomly varying slope. And so now I'm going from 10 parameters to 8 parameters, right? And the likelihood ratio test is 1.1 with 2 degrees of freedom. And that is also not statistically significant. But again, that's really, I haven't shown you model 6B yet, but that's really comparing model 6 to a model that it doesn't have a variance or a covariance in it. Yeah.
It doesn't test intercepts,
Doesn't test.
the ANOVA, like it
I
does.
mean, it could. We're not right now.
Okay.
It's a thing, when you do this, because I have a randomly varying slope, it is going to eliminate the randomly varying slope. So it's not eliminating the randomly varying, and that's what it means. Like single term deletion means it's taking out like one term, it's taking out the slope, the random effect for the slope, which again is one term, but it's actually two parameters because it's two taus.
And what would that be in the code that they're removing?
Or yes, it tells you right here. It says it's removing the random slope in this, right? So basically what it's doing is it's going from, see, it's saying, here's your model, and it actually spits out your model. And then it's saying, what I'm removing is, so this line right here tells you what it's removing. What I'm removing is the SES CWC in the random effects part of the equation. And when you remove that, then it's like saying you're going to one bar school ID. So that's how the RENOVA is working. And it's always going to tell you, it's going to tell you what your model is, and then it's telling you what I am deleting. So, I mean, somebody asked before, what happens if you have multiple slopes? I don't know. Well, we could run it and find out because it would tell us what it's deleted. It always does, you know? Yeah.
It does not look like BIC or other, so the default of the RENOVA, what's the difference between this and the ANOVA? Because it only reports AIC and LIT, so.
That's right. Yeah, it doesn't give you the BIC, right? It's just giving you the AIC and it's just giving you the likelihood ratio test. And the ANOVA, remember the ANOVA is actually computing everything using full maximum likelihood, and the RENOVA is going to use REML. So if you were looking at that and thinking that like the actual deviances look slightly different, that's why. If they're, I mean, again, the deviance differences don't really look different, but that's why the deviance. So far, so good. So model 6B, if I want to run model 6, so really, I just got a comparison of model 6 and 6B here. 6B, I said, was the one that doesn't have a randomly varying slope at all. No slope, no covariance. And when I run this RENOVA on model 6, it gives me a comparison between 6 and 6B. So I have that. I could also do it like the long way, right? And I could say, let's run model 6B. Model 6B. And then actually, I could run the ANOVA between model 6 and model 6B. Okay, here we go. So here's the ANOVA that compares model 6 to 6B. You can see this looks very similar to the RENOVA model 6 in the sense that it's still comparing a model with 10 parameters to a model with 8 parameters. The numbers are a little different here because this ANOVA is using FIML, not REML. But again, we get a chi-square difference of 1 with 2 degrees of freedom, which says, okay, I could get rid of the randomly varying slope and the covariance between the randomly varying slopes and intercepts. Those two parameters together, I get rid of them, and my chi-square only increases by 1. Or not my chi-square, my deviance only increases by 1. And that chi-square is not statistically significant. So this would tell me that I would favor the model where I don't have the randomly varying SES slopes at all. So like, not only do I not need that covariance, I just don't need the randomly varying SES slope, right? So this model 6B has 2 fewer parameters, fits about the same. Does that make sense?
Is there a RENOVA for model 6 would be so different from the ANOVA of 6B and 6 that we would come to the conclusion or never know?
I never want to say never, but I would say that like they should generally give you the same thing. Yeah. I mean, again, like, you know, one's using maximum likelihood and the other's using REML. So like, could I mathematically come up with an example where they diverge? Probably, but It would probably take some doing, it'd be hard. Okay. So here's my compare models. And again, you can really see when you look at when you just look at the deviances across these three models, you can see, remember, model 6 has the lowest deviance, but the change from model 6A to model 6B in terms of deviance is basically like negligible, right? So, and this is also kind of interesting. And this is the place where like either the test bar or doing things a piece at a time, I don't really care how you do it, but can be kind of helpful because what I see here is that chi-square change of 1, it really happened actually when I constrained the covariance to be 0. And once I had constrained the covariance to be 0, like there was basically no change in the deviance at all when I got rid of the variance component. Do you see what I mean? Right, so like this literally is like, and again, you look at this, look at 6A and 6B. Look at my fixed effects estimates. Well, okay, 1.0, I mean, they're close, right? Look at my variance components, super close, right? I mean, other than the fact that I don't have that 0.3 or 0.314, but it doesn't really seem to change. And that's also another thing you kind of want to, again, when it's your own data, I'm not saying you need to do this for your homework necessarily, but when it's your own data, another thing you want to look at is like, do my parameter estimates, do they change a lot when I'm like, because again, like if I don't need it and I get rid of it, things should generally look pretty much the same. And that's exactly what I see here. So like, that's another, another sign that like, it's no big deal to drop that random slope. My model fit doesn't get worse. And like my parameter estimates are basically invariant to whether I have that random effect or not. Right? If I ran this, and again, I wouldn't expect to see this if it's not significant, but like if I ran this and suddenly I had really different parameter estimates, I'd be like, whoa, well, I got to think about this, right? What's going on here? Does that make sense? Okay. All right. Time, by the way, how are we doing on time? I'm afraid to look. Okay. Oh,
It's 11:38.
that's great. Okay. So here are some more details on Renova, like sort of nitpicky details that, for different types of models that we're not even.
Well,
Good.
that actually, you answered the question in
Yeah.
that about if there's two slopes.
I think I did, right?
Yeah,
Because
you did.
it says,
That's right there.
I was going to say, I remember. Okay, so there it is. So what does it do? It says,
It takes one away and then the other away and tests all three.
yeah, so there you go. That's what it does. All right. So now, okay, model 6, we already did this, right? We already did all of that. Okay, blah, blah, blah. Okay, okay, so we could compare we could compare the ANOVA for model 6B and model 6, right? And I pointed out that that using Renova and using ANOVA looks a little bit different because one's using maximum likelihood and one's using REML. By the way, if you're interested you can do this, by the way, if you're using ANOVA and you don't want it to refit the model using FIML, which in this case would be reasonable because we're just comparing models that differ in terms of their random effects. Like again, it's not. If I cared, I can put in this refit equals false, and that will actually force it to, it will not force it. It'll just like stay with REM. It's not going to rerun with FIML. Okay. All right. So now, next. Okay. So like, here's where I was saying, what if I don't care that much about make such a big deal about parsimony? What if I don't care? I want to have a lot of random effects. And here's where I was saying, like, this is having lots of unnecessary random effects can really cause you model convergence or estimation problems, which I mentioned before. Okay. So now let us look at HSB2 for a sec. Or well, look at HSB2. HSB2, remember how I created HSB2 before? HSB2 only has 6 columns if you look at it. And I did that just because when we talk about the rates and stirba stuff, I think it'll be easier to kind of keep track of these 6 columns. So Column 1 is school ID, column 2 is math achievement, sector, SES, grand mean centered, SES, group mean centered, and then mean SES, grand mean centered. So that's my HSV2 data set. Okay. So now, let's see. Okay, now I want to run. Oh, yeah. So for simplicity, to show you some of this rights and service stuff, I'm going to run a new model. It's not going to be model 6. It's going to be just slightly different. We're going to call it model RS1 for rights and Sturba model 1. And this has a randomly varying intercept and a randomly varying slope, but I didn't put in the cross-level interaction between the slope and the intercept, just to keep the, I mean, it would be easy to do, but just to keep the code, just to keep things easy and simple. Okay. And then I have a tau matrix that actually estimates the variance of the intercepts, the variance of the slopes, and the covariance between them. So the only difference really between, I think, this model and the model 6 is I've taken out the cross-level interaction between the level 1 SES slope and mean SES. So if you look on your paper, where it looks a lot prettier than it does in our markdown, you can see exactly what the equations look like. And remember, we talked about rights and Sturba R squared before, right? And I said, if I don't have to worry about what kind of centering I use. If I just want to get the total proportion of variance explained, I can use uncentered or grand mean centered or group mean centered data at level 1. It doesn't really matter. But if I do want to get the rights and Sturba to partition the variance into the level 1 and the level 2 variance, then you really need to group mean center your level 1 variables and add the aggregate back in at level 2. Yeah.
So is mean SES only predicting
The intercept.
randomly varying intercept?
Yeah,
not
so-
randomly-
Exactly. So going back up here, this is a model where I have this, but I don't have this. Yeah. That's right. And if you look at the code, you can see that, right? I've got math achievement is predicted by the within SES slope and mean SES, but I didn't put in the cross-level interaction between, so I'm not allowing mean SES to moderate the effect of SES on math achievement. And you can see here that I've got the SES slope is randomly varying. Okay, so I'm going to run this model. Now I want to show you actually how you can get Sturba stuff. Okay, so here's our model. So you can see this is actually, I took out some other stuff too, right? I made this a much simpler model because I'm going to walk through how to do the rights and Sturba stuff kind of a long way. So here's my model. And now I'm going to compute the rights and Sturba variance components for the R squared measures like by hand, which really means in R, but by hand, so that you can kind of, again, so I think you can see where they come from. And also because honestly, the rights and, you think the test bar, wait till you try the rights and Sturba R package. It's also a little buggy. So, but it's okay. It's not so bad because all I need is to compute 3 of these 5 variance components, right? F1, F2, V, M, and S squared. This S squared, that is my residual level 1 variance. So I have that. M is my between cluster variance and intercept. I have that. So all I need is to compute F1, F2, and V, right? And again, you probably don't remember this from the PowerPoint, but it's actually not so hard to compute these. The F1 component is really just gamma. Remember that? This is why it was in a reduced model, by the way. It was, remember how it was gamma, V, gamma? All that means is take your fixed effects, right? Take those parameter estimates for your fixed effects. V is actually going to be like the variance for this level 1 predictor here times the fixed effects estimate. So the first and last blanks are just your gamma, they're just your fixed effects at level 1. So it's going to be the effective SES on math achievement at level 1. And in here, we're just gonna compute the variance of the level 1 variable. SES. So again, that doesn't make a lot of sense to you. Don't worry too much about it. Just trust me that this will give you the F1 component. So F1 is just, again, fixed effects estimate times the variance of the variable times the fixed effects estimate. And when I do that, this is kind of cool. So I've written out copious notes for you about all of that. Da, da, da. Here we go. What does that look like? And this was in the chapter that you had to read, I think, that I wrote, right? So what does that look like? This is a gamma 1 naught, 2.193 times, and now you see why I created that HSB2. HSB2, this comma 5 means compute the variance of the 5th column in the HSB data set. That's what that means. And that's why I created HSB2, because I was like, I don't want to keep having to count all these columns. I want fewer columns. So, and this is variance. Just create the variance of the SES group mean centered. The T here means transpose. So it's gamma transpose V gamma. And I do that. And I'm going to get something. I'm going to do the same thing, actually. At level 2, it's going to be the gamma for the level 2 variable. So it's going to be the gamma not 1 for mean SES times the variance of mean SES times the level 2 coefficient. So here you see, this is gamma. If you look back at the output, this is the gamma for the effective mean SES on the randomly varying intercepts times, again, HSV2 comma 6. This is where mean SES sits in my data file. And I'm just saying, take the variance of mean SES and then multiply it by the gamma again. And I get F2. And then finally, I only need 3 of these pieces. And then once I got my 5 components, I can put them together however I want. Then I calculate this V variance component, which is the unexplained slope variance covariance. And so this is just going to be the diagonal. It's going to be the tau matrix, excluding all the elements that have to do with the intercept. Because again, we've got a piece for the intercept. And then the variance. So scroll down here. Show what that looks like. Okay. Here we go. Where to go? F2, V. Where's my V? Oh, here it is. Here it is. So here's my V. So again, I'm just telling it. This means I have variance components. Ooh, I hope I ran this. I created a variance covariance matrix for RS1, and I'm just telling it which variance I need here. Let me go back to the variance components. I didn't run it. Here we go. There we go. So I'm saving as a data frame the variance components for this model. And you can see, if you look at this, it's a data frame that has 4 rows and has 5 columns, right? Column 1, 2, 3, 4. So column 4 has the variance covariance matrix and stuff in it. And then I care about, right, the CWC, I think it was, right? So yes, because it's randomly varying slopes. So I'm going to be looking at, here we go, CWC. So that's going to be row 2. Row 2, column 4 is 0.6858255. That's the variance of the randomly varying slope. So when I say 2, 4, here I just say, oh, in this data frame, grab out column 4, row 2, column 4. Row always comes first, by the way. Row 2, column 4. And I'm grabbing that out, right? And so now I'm just saying, okay, I'm going to sum the traits again. I know you don't care about this, but it's actually not that bad. I do that. This 1 by 1 just means that this thing is a 1 by 1 matrix. So it's just telling the dimensions of my scalar, which is 1 by 1 here. So that's why that's that. Okay, I do that. And now I've got V. And really cool thing is, I don't know if I ran everything. Oh, here's my M. So M, notice I just grabbed that out of the same data frame because M is just my random, it's just the random intercept variance. And I can grab this out of that data frame too. It's just my residual level 1 variance. And now, finally, oh, I didn't run F1. My bad. Hold on, let me go back up here. Where's F1? Okay, here's F1. Let me run F1. And I promise you, you do not have to do this by hand. But I do think it's actually super helpful. Oh, I didn't run F2 either, I guess. F2, here we go. I do think it's super helpful for you to understand where all these numbers come from. Okay, so there we go. So now I've got those 5 components, and here they are. It's, you know, in the order which I said it. So FB, F2, F1, and F2. And I can just add those up to get the total variance. And this is what's really cool. I add those up to get the total variance. And what do I get? It might not be spot on my actual variance because this is model implied variance, but I get 47.75. And now if I actually look at the standard deviation of the outcome variable 6.87, so if I square that, I get 47.31. So it's really close. Do you see that? Yay. It's really close to that. Okay, this is what I just estimated the total variance in math achievement is. Yeah. This is, I just went back to my sample and said, oh, here's the standard deviation. If I square that, that's the variance. Like my model implied variance should be really close to the actual variance, right? If the model implied variance is not close to the actual variance, that would suggest that my model implied, yeah, my model is not implying the right variance, right? There's a problem with the model in some sense, right? So that's also very sort of diagnostic, right? And in fact, well, and yes. So I can see that those are pretty close. I'm really happy about that. And now that I have all these different pieces, I can just like, it's basically like I can plug and play. I can be like, oh, what proportion of the, you know, I can say what proportion of the fixed effects variance explained is explained at model 1. And that would be like F1 divided by F1 plus F2. I mean, basically, I can just ask myself, what proportion of the variance is blah, 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 right? But remember, I said, I really care about the proportion of variance that's explained by the randomly varying slopes. Do you remember that? So let's go to that for a second. So I've got the proportion of, I can do this. I can say what proportion of the variance is explained by the level 1 fixed effects. It's 0.04. The level 2 fixed effects, 0.12. But here's the thing that, like, again, is really useful. What proportion of the total variance is explained by the random slope variation and covariation? Because remember, I'm trying to figure out, do I need this slope to randomly vary or not? And in this case, this is saying that 0.0063 basically is the proportion of variance explained. So that would mean that my randomly varying SES slope is explaining about 0.6% of the total variation in math achievement. So then the question is that big or is that small? I don't know. I mean, it's small. It's not, I mean, I've seen smaller, right? It's not big, it's pretty small. And remember, I haven't even put in any kind of predictors of that slope variance. So this is literally like the unconditional SES slope variance, if you will, right? So at most, right? I mean, like the slope variance is, you know, even though this is a residual, it's, you know, again, it's sort of the total because we haven't used any level 2 predictors like mean SES or sector to predict the variability in the slopes. Okay. Questions? Is this okay? Oh, 5 minutes to spare. Questions about any of that? Does that make sense? So now, last thing here. I could actually compare. Remember, we talked about like the Rodenbush and Bright stuff, right? So I've got a whole bunch of, you know, computations here, but remember we had like Rodenbush and Breik, we used that proportion reduction and variance at level 2. So, but for that, for Rodenbush and Breik, I have to have another model. I have to run some sort of a model where I compare these two models to each other. I can't just run, like, that's a nice thing about Wright Sturba. I can do it on one model. So here for RS0, I basically have, let's see, SES, centered, but I took mean SES out of the model. So the question here is like, what proportion of the level 2 variance, right? So what proportion of the variance at level 2 is explained by mean SES? That seems like a reasonable question, right? And one way that I could answer that question would be just to run this model and compare the two models using that R squared at level 2 function. R squared at level 2. Okay. And this says, so what I did here is I said, compare the model without mean SES to the model with mean SES in terms of what proportion of the, again, this is like the intercept variance. What proportion of the intercept variance is being explained by mean SES? And when I compare those two models, I find that it's like about 69% of the variance. And again, if you look at, it's just tau not for the baseline model minus tau not for the fitted model divided by tau not for the baseline model. So if you look at that, you'll see that the tau not goes from, I put it in there, but it goes down substantially. And basically, we're explaining 69% of the variance by me in the between school variability and math achievement using the SES of the school. Which, stop and think about that conceptually for a minute, right? So what we're saying is, knowing schools of higher, like knowing whether school is high or low SES actually explains almost 70% of the between school variance in math achievement, not the total variance, the between school variance, right? But that's a lot. But what about, I could do the same thing with just one model in the Wright and Sturba framework by just running, right? I could just run, let's see. Okay, here we go. I can run this model again. And somewhere here, where's my, oh yeah, here it is. And oops. Let me show you the shortcut. Where to go? Right, since Sturba. Okay, here it is. Here it is. I can run it in Wright and Sturba using this R2 MLM package. You don't want to do everything I just did, but you probably don't. There we go. And it will give you this. Ta-da! So this is kind of nice. So it basically, what it's doing is it's computing for you those 5 components that we talked about. If you go back and look at my R markdown, you'll see these numbers match exactly with what I got for F1, F2, B, S squared, and M. They're exactly the same, right? And then remember I said that the between is really F2 and M, and the within is the other 3 components. So when they come up with, sort of what the decompositions are, that's what they're doing. They're saying the between has these 2 pieces, the within has these 2 pieces, and they decompose. And then you can see that basically we get like what proportion of, we can say what proportion of the variance, the between variance, is explained by, let's see. Oh, I think I ran the wrong model because I don't have any between variance. Oops. But anyway, I could do this and say what proportion of the between variance, what was it that I wanted? Was it 0? Oh, it wasn't 0. What's the name of my model?
Was it RS1? Is that what you're talking about?
Oh, RS1. No, I think I wrote over my RS1.
RS1.
I know. Okay. Yeah, I did the wrong model. But okay, hold on. Well, you get the idea. let's see here, hold on a sec. RS, where's my model? Oh yeah, model RS1, thank you. Oops, it's way up here. I should have run it way up there.
So while she's doing that, I will just give you all a hint that if you are running R2 MLM, and your like little plots window isn't big enough on your screen, it may kick you out an error saying like the boundary, like some boundary error, just make that window bigger and rerun it. I fought with that for a really long time until I figured out that
There we
that's
go.
what I was talking about.
There
So
we go. So there you go.
don't go through what I did.
Okay, so here it is. Now that I ran the right model, you can see that, remember how we had 69% with the Broad, Butch and Bray? We have like about, again, it's not, they're not gonna be identical, but they're gonna be close. If they're not close, that's diagnostic. That tells you, I better think a little bit more about all of this. So that's how you do this. Yes, this is buggy. Writes Sturba, the package is buggy. I think this is a big advantage of using our Markdown, because I had the same problem.
Yeah.
With, because the graph, and there's no way to just say turn off graph, because I was like, I don't care about the graph, I just want to turn out the graph, but it was not an option. And I'll also tell you that I had problems sometimes getting the within and between decompositions, depending on the way that the data frame was saved in some sort of weird and subtle way that I'm not sure I ever totally diagnosed. But that doesn't matter for you for homework, because we're not asking for the within between.
Right.
Because I'm also not super enthralled about it doesn't, as I said, it doesn't always work well when the cluster size is small. So for homework, you only have to do the total, and that always works fine. So that shouldn't be a problem for them. All right, that's it. See you next week. Oh, wait. There was the thing, right? So someone had asked if I could do an extra review session of conceptual things for the first few weeks. And I can do that. I will do that on Monday at 8:30 in the morning before office hours.
Virtually, right?
Virtually for people who can join, and I will make sure to also record it. So I will do some review of conceptual stuff, bring any conceptual questions you have. And and I will answer questions, and I will sort of revisit all of this stuff one more time for those who are feeling lost.
And based on just office hours, it feels like people who haven't had SEM tend to have more of these questions. So if you just came from regression, it might be a really good idea. Not that anyone else can't go.
Yeah, that's a good point, because I think, some of the model fit stuff I think is the same logic used in SEM, so.
Thank you.
Thanks. Question? Yes, let me just go through this.
Yeah.